Ladies and gentlemen, welcome to the Perform and Liberate webinar titled Organic Electrochemistry Towards a Sustainable Chemical Industry in 2030. My name is Eddie Vidal and it is my pleasure to be your host for this event. The two European projects, Perform and Liberate, have joined forces to address the industry innovations regarding the use of bio-based feedstocks as well as the new challenges ahead. We know you could be anywhere else right now. We're all busy. You have meetings, you have phone calls to attend to, so thank you for having joined us. Now, the webinar will be structured in three different segments. The first one will consist of three plenary lectures by renowned experts in this area. Ms. Ángels Orduña-Cao, Executive Director of Aspire, Professor Siegfried Waldvogel, who is from the Johannes Gutenberg University, Mainz, and Mr. Carl Friedrich Hoppe from Evonik Industries. The second session will address the challenge of using bio-based feedstocks as a chemical source with presentations that will examine the use of low-cost lignin feedstocks in high-value biosustainable chemicals, among others. The speakers will be Mr. Bernd Wittgens, Mr. Roman Latsusbaya, and Mr. Bart van den Bosch. And finally, in the third session, we will hear three presentations regarding the new challenges that the electrochemical industry faces, such as the development of added value products by electrocatalytic oxidation of bio-based platform molecules, the case of glucose oxidation, or greening API manufacturing with electroorganic synthesis. The speakers will be Mr. David Cantillo, Mr. Jost Helsen, and Mr. Gabriel Centi doing their presentation together, and Mr. Stefan Krawilitsky. For the next 4 hours, these projects will review the current state of the electrochemical industry and showcase the ongoing innovations that will lead to a reduction of CO2 emissions through the efficient utilization of bio-based feedstocks and renewable energy. Now, after the speakers of each session have given their presentation, we will have a brief question and answer time where we will be taking questions from our viewers through the platform, through our chat. If we do not have time for all of the questions, the presenters will answer them directly in writing, so we encourage you to participate by posing your questions. Let me explain to you that in order to ask your question, if you're in the full screen, which is probably the case, if you exit the full screen, you will see some of the icons on the bottom, which include info, where you will find information, including the program. You will also see one that is chat, where you can make any comments that will be seen by anyone attending this webinar. And finally, Q&A. That is where we'll need you to click and ask your question. And please, if you can, indicate who the question is for. As I said before, we'll be taking the questions after each one of our segments, our plenary session, then our session 1, and our session 2. After the speakers have finished, then we'll go to the questions, and we hope to receive questions from you through the Q&A. So be sure to take advantage and participate. Now, very quickly about the organizations that have brought us this webinar. About Perform. The expected impact of the Perform project derives from its multi-level approach that includes a combined integration between electrification, reduction of process complexity, avoiding the use of co-reactants through system integration, innovation in processes, and bio-based use of feedstocks, as well as the development of a flexible power platform pilot plant platform. Perform is expected to contribute to technology development to reduce the environmental impact of the chemical industry. The technology developed in Perform will reduce CO2 emissions from the production of chemicals due to the efficient utilization of renewable bio-based feedstocks and renewable energy. It will also be essential for a future sustainable society that uses local resources. About Liberate. The LIBERATE project aims at designing an electrochemical plant to demonstrate the commercial opportunities of converting low-cost lignin feedstock into high-value biosustainable chemicals such as vanillin, antioxidants, or polyamide. Now about SPIRE. Both projects, PERFORM and LIBERATE, are funded by the European Union Horizon 2020 Research and Innovation Programme, and they are also part of SPIRE, a European association committed to managing and implementing the SPIRE public-private partnership. The mission of SPIRE is to ensure the development of enabling technologies and best practices along all the stages of large-scale existing value chain productions. Now, after these opening words, let's move on to our first session and our first speaker. As I said, this is our plenary lecture session, the first. And first of all, the first presentation will be by Ms. Àngels Orduña Cao. She is Executive Director of Aspire. The title of her paper is Processes for Planet Towards the Next Generation of Process Industry. Now, the presentation will focus on what are the EU process industry's ambitions, reflected in Strategic Research and Innovation Agenda, the SRIA 2050, and how this SRIA will determine the calls of Processes for Plants Partnership under the Horizon Europe program. So, Àngels, the floor is yours.
Thank you very much for this wonderful introduction. Hello, can you hear me?
We can hear you and see as well.
Okay, thank you. And you can see the screen also, I hope. Thank you very much. So thank you again to both projects for inviting us. Indeed, there are two projects funded under the Aspire partnership, of which the association Aspire is the private partner of the association. But now we are moving also into Processes for Planet, which will be the successor of Aspire partnership under Horizon Europe. So Aspire was funded under Horizon 2020, and Processes for Planet is funded under Horizon Europe. So I will explain you a bit, what does this all world imply? So under Horizon Europe, you can see there will be three types of partnerships. The institutionalized partnerships, which are very much regulated in terms of the legal framework, the co-funded partnerships, in which, let me mute myself so I make sure I don't hear myself. Okay, so the co-program partnerships are the ones that simply we sign a memorandum of understanding with the Commission, and then the funds are available and open, the calls are available and open to anybody, while the co-funded partnerships, the money comes partly from Horizon Europe and partly from the member states. It's a bit more complicated, the participation, because here you need to have, depending on which country, it will have different rules of participation. So we are a co-program partnership. We will sign the memorandum of understanding with the European Commission, which is our public partner, on the 23rd of June. So we represent the private side. This means 10 sectors of the European process industries. And then from the side of the Commission, it's DG R&I, the leading DJ, but also DG GROW who participates in this contract. In terms of Horizon Europe, we are embedded directly within Pillar 2, and specifically within Cluster 4 on digital, industry and space. Though we certainly see also big alignments and big connections also with the Climate 5. Important, every partnership has an envelope, a funding envelope. So the partnership support the Commission in developing the calls within that partnership, and then the Commission provides a funding envelope for those topics. In the past, for Aspire, we had 950 million, and now we are moving to a partnership funded with 1.3 billion exclusively for projects. And that is 27% more than under Horizon 2020, which we consider a big commitment from the Commission with this partnership. So that's important. Also an important point, we have moved from 8 sectors. We were created by 8 sectors in 2012. And now in 2020, we engaged 2 new sectors, refining and pulp and paper. So that's also an important change, a move ahead for our partnership. Let me go to the next slide. Let me explain you a little bit what does this partnership thing means a little bit further. So as I said, we have a public partner, which is the Commission, and then we represent the private partner. So as an association, we don't receive any money from the Commission. So from this 1.3 billion funding envelope, this goes entirely to projects. And we sustain ourselves through the membership fees applications, which are annual. And then we have, of course, a General Assembly, we have a Board of Directors, we have a support office of which I am the Executive Director, and then we have an advisory group, and we have several working groups that work together to provide the input of the processes for planet topics. So we organize several activities with all our members to build that content, to build the priorities, to develop the topics, and then to discuss them with the Commission. Where do we discuss the priorities and the topics with the Commission? We discuss them at the Partnership Board. The Partnership Board is the space where ASPIRE, on the one hand, and the Commission, on the other hand, meet and discuss on the priorities, on the topics for Horizon Europe, but also it's a bit wider now, I will explain later, on all the priorities of this partnership and how to implement them. Yeah. So if any feedback from our members, any discussions that our members have here in the working groups and that are approved by the Board of Directors goes to the Partnership Board for the discussions. But then under the new framework of Horizon Europe, the co-program partnerships will also have some external advisory. You need to understand that this ASPIRE advisory group is an internal advisory to the association. So only our members have access to be part of these groups and advisory group. But externally, we have a kind of what the Commission calls an external advisory committee. The name could be debatable, but that's the formal name. And in our case, it has 2 panels. One is the feedback panel. It's the space in which ASPIRE and the Commission will discuss with civil society. So that is discussions with NGOs. So we expect from them to receive informed feedback that we will consider from ASPIRE in the discussions to see, okay, how we can embed it into our proposals or not. But they are not a validation panel, so it's just a discussion panel to receive their feedback. But then very important also for all our members, it's the impact panel. The impact panel is a space in which we want to meet, again, ASPIRE members and the Commission with further funders and investors. So with everybody, for example, with the Innovation Fund, with member states, with the European Investment Bank, but also with any other type of funder and investor that can help reach our goals. Because you are aware, I imagine, that Horizon Europe only supports up to TRL 7 or 8. However, in our roadmap, we have defined up to TRL 9. So it's important to find the right support to move from TRL 7 to 9. And that's important for those projects which are already mature to move forward. Let me see. So why the change from ASPIRE to Processes for Planet? That is very simple. That was a prerogative from the Commission to all the partnerships. So all the partnerships we have needed to change the name. But then, again, we need to, we developed a roadmap or a strategic research and innovation agenda, ASRIA, and we developed it with our 10 sectors. I would like to remark one thing. We always say we are a unique cross-sectorial community. What do we mean by that? In other partnerships, there are also different sectors involved, or companies from different sectors involved. However, in ASPIRE, we say we have a sector on board only when we have the industrial association at European level on board, plus companies of that sector. If we only have companies, we cannot consider we have the sector on board, but also if we only have the industrial association, it's exactly the same. So this is kind of the unique characteristic of processes for Planet Aspire. But we have other companies from other sectors like IT, like textile or other that say, hey, but we can also contribute and we can also benefit by being part of processes for Planet Aspire. But then in our roadmap, we said, okay, we started by the end point. Huh? So we said, what is the impact that we want to create? Of course, our impact needs to be fully aligned with the European Green Deal, and it is, and with the Circularity Action Plan of the European Commission, of the European Union. So our ambitions are three. One is the climate neutrality, so reach the net zero emissions from the process industry. Another one is related to circularity, and it includes a twofold ambition, which is to reach the near zero landfilling, but also the near zero water discharge from our industries. And finally, the third ambition is on competitiveness. So of course, there is no industries if they are not competitive, no jobs if the industries are not competitive. So this is really very important. So how have we done that? We have developed a roadmap that includes 14 innovation areas and 36 innovation programs that work from the technological aspects to the non-technological aspects, so including skills, including framework conditions, but you can see here industrial urban symbiosis, renewable energy, etc. Then this is the basis of all, but as I said, our roadmap defines from TRL 1 to TRL 9. So what happens beyond Horizon Europe? We have two key initiatives in our roadmap that intend to reach the TRL 9. One is the first of a kind plants. So these are pioneering plants that do not exist there and that can really help us achieve these net zero emissions, but also the hubs for circularity, because the impact happens somewhere. I will explain further on this now. Just here very quickly, the summary of which are the innovation areas so that you can see it a bit better. You can see that the main points are industrial urban symbiosis, process innovation, which includes points such as electrification, energy mix, the CCU, resources efficiency, flexibility. Digitalization is also a very important point. And then, as I said, the non-technological aspects. And we have foreseen a progress of achievement of the different innovation areas and programs according to the information we have right now. So these 36 innovation programs, I'd like to reinforce on the three ambitions. So for the ambition of net zero, our roadmap includes solutions to move from fossil fuels emissions to green processes through the efficient integration of renewables and through the valorization of process emissions. So the processes will need to be adapted to cope for alternative resources and to have disruptive innovations for that. And then on the circularity ambition, now, our roadmap includes important proposals to move from today's scenario, landfilling, incineration, recycling. Recycling is not that it is to be avoided, but it's not the only solution, to upcycling, what we consider the future scenario. What do we mean by that? We need to avoid to stop at waste. When we discuss with the municipalities, for example, they only talk about waste. No, we want to move this waste into new resources, but we need these resources to keep the same quality in the same loops, so that they can really be reintroduced in bulk amounts into the industrial systems, into the industrial processes, and transformed again into new materials. That could be a very good part of the circularity solution. But also, this is a solution for all the waste that is out there right now. But then also, what about the future waste? So our roadmap also includes proposals on the eco-design of materials through innovative processes, so that these future materials are free of toxic elements and can be upcycled more easily. Of course, here, as you can see, we see this as part of the value chain. So we will need to also discuss with the manufacturing industry, with the ones who make the cars, the house, our smartphones and everything, right? But also because then it's important that afterwards it can be very easily disassembled. But then we will also need to work with all the collectors, sorters, recyclers, so with all the waste management sector. So that will also be very important. Here, as I say, in competitiveness, I will only highlight two things, and that is that we need to de-risk the investment. So an important point there here for our partnership will be to unlock the private investments and the barriers to market for the climate neutral and circular solutions. And that requires different solutions. I'm not going to rebound more on these, but I think it's important. I will explain a bit on that later. Let me go to the two key initiatives that I mentioned before that go beyond TRL 7.8. The first one is the first-of-a-kind plants. So the first-of-a-kind plants are the first large-scale plants in operation. So these, all our sectors coincide in saying that a single technology developed by any of our projects will not be able on its own to help us achieve the net zero emissions. It is a combination of different technologies into a first-of-a-kind plant that can help us do that. But also in Europe, we have a very extensive industrial park. So we also need to change the way the existing plants work. So we also consider first-of-a-kind units within the plant that will help work that plan in a completely different way. So that is very important, and this is for us a very important step ahead of our partnership. And we have identified already 50 marbles, we call them metaphorically, and we intend to launch 15 from the period from 2021 to 2030. Let me go to the second initiative beyond TRL 7, which is the hubs for circularity. In reality, there are hubs for circularity, which are at different stage levels. But of course, the aim is that they all reach the full integration and TRL 9. So the main motto here is that impact doesn't happen in the air, impact happens somewhere. So we need to gather the regional community. We consider the hubs need to gather the regional community, the industries, the research and academia, the public sector, the civil society, even the financing sector, and then define what are the needs of the region. They need to define this sustainable business model, what we call a business to territory plan, and then identify which are all the needs. Part of the investment should come from the industry, from the process industry, and it can be material design, digitalization, process innovation, disruptive innovations from the process industry, but also from other industries, because we are not in silos, so we work in a value chain. But then also some other co-investments could come from the member states, the regions, the municipalities, for example, in waste management plans that will help achieve the circularity goals of the region. For that, we understand that the regions need to be connected and need to have access to specific information and need to have these tools available. And we want to create this European community of practice, which is in one of our calls within Horizon Europe, to gather all these tools that we will put available to the different hubs for circularity. Aspire aims at acting as a kind of umbrella to support the hubs for this exchange of information. And of course, we will collaborate very closely with the winning consortium of this topic. This is more based on the non-technological aspects. I would only like to highlight that among the different actions, so we expect a lot of support and collaboration with especially with our academic members to bring all the skills into the curricula of the universities, but also not only of the universities, because we aim at defining or identifying which are the re-skilling needs of all the workforce of the process industry. So not only the high level, but also the people at the plant, so everybody. And for that, we also have a project which is Aspire Science. It's supported by Erasmus+, and it's a consortium formed by mostly by ASPI members that works specifically on industrial urban symbiosis skills and on digital skills for that. We are part of a value chain of the partnerships. I see I'm running out of time, so I will not extend myself very much on that. But the same way I said before that we are part of the value chain. The different partnerships also represent the different parts of the value chain, and we aim at generating a circular value chain, which is very important. Here you have the topics of processes for planet and the Horizon Europe. The Commission will be published them finally, officially on the 22nd of June. The deadline for processes for planet projects proposals will be on the 23rd of September this year and on the 30th of March in 2022. So here you can see that this year you have topics on the deployment of industrial urban symbiosis solutions. It's important to understand that we have had several calls under Aspire on that, and this builds further from that. So we always take care not to repeat, but to learn from the projects and then move forward. Then also you see here the call for the European Community of Practice, another one on the design and optimization of energy flexible industrial processes, and then another one on circularity of composite materials. For 2022, you see also that we focus on circular flows for solid waste in urban environment, on the valorization of CO2 streams, but also on new electrochemical conversion routes and on the integration of hydrogen, which is also a very important point, sorry, in the energy mix that our roadmap presents. Just two more slides very quickly. I would like to emphasize the importance that our members highlight of being part of this community. All our sectors have said that this continuous dialogue that they are having through the working groups, through the advisory groups, through the board, with the Commission, in the different workshops, in the different events that we organize for them, are very important for them to understand which are the common problems across sectors, and which are the common solutions that they can develop, or the solutions that they can transfer from one sector to the other. But also for the SMEs, it's very important because they are also accessing directly through their customers. It's a very interesting point I would like to emphasize on the SMEs, because in other partnerships, the SMEs receive the innovations. In Aspire, what we have perceived is that our SMEs are providers of innovation. So in our roadmap, they see their market opportunities, but then also by participating in our activities, they are able to get in direct contact with the large industries, which can be their customers, even to develop the solutions together. It's true that anybody can participate in the projects, even if they are not members of Aspire, but I can tell you that the SMEs that are members of Aspire are growing above the average of the EU, because they are really finding opportunities. And it's true also that the more active you are in a partnership, the more benefits you will get. So that's also very important to highlight. But also the access to a pool of talent also in the research members, it's also very important. And for them, the link to this access to this applied innovation that they are worked also in a university, they do their best, but it's not always so immediate. So for them, it's also very important. And then to become a member here, you can have the link. You will receive the presentation, so you will be able to explore it, and you can contact me at any time. Just to finalize, I would like to highlight some of the events that we do yearly, and of which our partnerships, our members profit or take benefit of. So every year we organize for our members a Processes for Planet brokerage. The first one of Processes for Planet, it was in February. But then also we organize different workshops with member states in which our members also can participate and also listen directly and have this direct interaction with the member states. Then we also have specific thematic workshops or community workshops to discuss on the priorities, but also to identify which are the transfer, to build knowledge, I would say. I think that would be the best way to say, to build knowledge together. And we are now defining a new structure that will allow our members not only to build knowledge from a top-down perspective, from the board to request what they want, but also for the members to bottom-up say, hey, why don't we discuss on this? Why don't we prepare a workshop or a specific thing on this? And this is very important. In our next event, so as I said, on the 23rd of June, it's the R&I Days, and we will sign we will participate in the MOUs ceremony with all the partnerships. And then on the same day, we will have our launch event. That will be a virtual event with the CEOs of our companies to showcase their pledges on climate, which will be very important. And then in October, we will celebrate this ASPAC community event to build further on the priorities that should determine the topics of Horizon Europe of the second work program. So we will start already working on that by the end of this year. And then in November, we will have a SPIA Projects Day, because we always look at the projects, and we always build on the results and on the learnings from the projects. And then these processes for planet stakeholders, so we also open a bit to potential newcomers so that they know us a bit better. From July to December, we will be kicking off the new partnership board, the new advisory and working groups, and the new feedback panel and the impact panel. So you can see we will not get bored until the end of the year. That was all from my side. Happy to answer any question.
Thank you very much, Angels, for this very detailed explanation with lots of information that I think will be valuable to everyone. Now, after hearing Angels Orduña, from the Executive Director of Aspire, it is now my pleasure to introduce our next speaker. That is Mr. Siegfried R. Waldvogel, sorry, I'm bad with names. Mr. Waldvogel is a full professor at the Johannes Gutenberg University of Mainz, and he is going to be talking to us about electro-organic synthesis, a 21st century technique. So I now give the floor to Dr. Waldvogel.
Thank you very much. Thank you very much for this really nice introduction. I will talk a little bit about the future technique, and we call it electro-organic synthesis. And the reason why this, I hope this works now, is becoming more and more interesting. It's because we are changing our electricity system. Conventionally, we use the coal and gas firing, fossil fuel. We should stop doing that. And of course, many countries, especially Germany, switch off their nuclear power plants. And that means we rely more and more on regenerative versions, especially wind power and photovoltaics. And these do not fit in the supply to the demand. And therefore, we need, on one side, definitely to have a larger storage device for electricity, but also that we make a little bit more electricity and we use that to make valuable chemicals. I think this is very important. Therefore, the question is, why is the electrosynthesis so important? Well, on one side, it's inherently safe. That means if you switch off electricity, there will be no one-way reaction. And I think this makes it very, very interesting. You can circumvent a lot of metals. You don't need them anymore. You bring in electrons, take them out on the other side. It means you have virtually no reagent waste. And of course, it can be more reductive than lithium and more oxidizing than fluorine, but the important thing is you have new synthetic approaches, and this makes it very interesting for companies and new applications. These are more political terms. The Americans call this disruptive technology and game changer, and indeed, this will be the case. Usually we use in synthesis a round bottom flask. This is the typical container we have. Then we use instead of that 2 electrode arrangement. You see, 2 electrode, not 3 electrode arrangement, because it's easier to use. And for molar conversion, you will see you need about in the range between 0.4 to 0.6 euro cent for in energy costs, even if you buy it as private person in Germany. That means the costs are affordable. On the other side, the amount of electricity depends a little bit on the molecular weight, but usually it's about 2 kilowatt hours per kilogram. What can you do with that? Almost everything, which includes oxidation reduction, but also you can have radical reactions or sequences, but you can also exploit the basic features of the radical anions. Important thing is we are not so much interested in the current voltage curves. We are interested in the accumulation of product, and following up reactions have to be controlled and designed that you do not have reversible steps in between, and then you can use a simple design for electrolysis. What can we do? Everybody's talking about synthetic fuels. Unfortunately, I have a guess this will be not a good business, because here you have to invest a lot of electricity, and large volumes, and a bargain will be small. Commodities will be complete different stories, because here you have a smaller amount of electricity, smaller volumes, and definitely a little bit more of return of investment. And for fine chemicals, it's already paying off, and this is already a realistic scenario. What most people don't talk about is the selectivity. Here you don't need too much selectivity, and therefore, because here you can accept even isomers. In some cases, even for polymer, because this is viable, but it's not viable definitely for APIs. Therefore, you need a very good quality here. And the second point, which is not usually discussed by many people, is the downstream processing. This is usually the killer of all process, because it's much more expensive than the electrolysis itself, if you have to afford something which is in this area more than the distillation. And here with API, like the biopharma synthesis, which is used for phenol, you can afford even a column chromatography, but then the product has to be quite valuable. We try to wrap this up when electrosynthesis is paying off, and then you see there will be a range where you can easily do that. And therefore, the point is definitely have a look what you do with that, and then you will find the market. I will tell you today 3 very short stories that we use solvent control, electrode control, and upcycling pollutants. You have only 3 ways to operate an electrode. One of them is that you have an inert electrode like graphite, platinum, or bonded diamond, or you have a catalyst on the surface, or you have a mediator which is involved. But this is then something which is difficult for scale up, because you have to pump it through flows as well. The most important slide comes here. Here you see you have on one side, you have the conversion at the electrode. This is an electrode stream. And after that, you have some other reactions which are following up. And this is very, very important. It means this is the ticket to the party. If you don't have access to that, nothing happens. If you screw up in between on the party, you don't make it to the end. Therefore, you have to control both parts. There's none of them is more important. And there are many parameters which are associated. That means you have a lot of parameters which are on this part, and some of them which strongly influence this part here. Also, there's some which are influenced both of them, like the current density, which indirectly control the potentials, but also the concentration which is formed and determine the pathway which is occupied. Therefore, the important thing is definitely we have a lot of parameters. How can we find a maneuver to find the the best operational conditions. And the way we do it, we use the so-called driven screening by product-driven criteria. We use different electrode materials. We have a kind of a setup we developed almost 10 years ago, or more than 10 years ago, and which is now available by ICA. The important thing is you have in this system directly a lot of material which is converted. You can directly isolate it out of the system, and it gives you very precise information that is later on very important. Beside the electromaterials, we look on the electrolyte combinations. You can think about almost infinite number, but keep in mind we mostly have collaboration with industry and for doing applications. That means we have to look at the wastewater stream and also about the safety issues. Therefore, usually we have a set of 5 to 8 which usually do the job. And control is already done by chromatography coupled with mass spectrometry. The precise or accurate data we get out of the system can be directly used for design of experiment with a minimal set of experiments, and this is also combined already with machine learning. Therefore, this is the heart and the backbone of our chemistry. When we have this is the undivided cells. We have 8 of them on one magnetic zero. This is a trade-off to get good quality data and also make enough electrolysis in an independent fashion. Then we know which kind of prep cell is working in batch type, and then we can go even to a larger batch type cell. Here the scaling factor is already 300 directly from the screening to this kind of stack type batch cell. If you go to larger cells, then you have a flow cell and there's no way out, and you need a little bit more periphery to operate that overnight. That means more or less that we, the heart is definitely that we have here our screening, and after screening, if we have the operational window, which is possible that we can make the electrotransformation, can isolate the product, then we go into larger batch cells, a couple of liters, maybe a 1 kilogram product. This is viable. If you go to larger quantities, then you have to go to flow cells, which is a little bit different scenery, but the information which is gathered here is very important for this pathway as well. The first story is about biorels. You find them almost everywhere: natural product, electronics, bioactive compounds. The important thing is this was a playground here to make some biorels, and these biorels were some building blocks for ligands to do hydroformylation with earth-abundant or more earth-abundant catalytic metals. And how to make this kind of biorels, there's a common way which was also awarded by the Nobel Prize, which was given to Suzuki. Here you have leaving groups on both parts of the areoles, and then you make a palladium catalysis, but you make you need multi-steps to make the starting materials. You need the expensive catalyst, and you generate some waste, which is difficult to get rid of in the EU especially. And on the other side, there can be a direct oxidative version, but here you need large quantities of oxidizers, and this generates a lot of waste. Therefore, electricity would be the perfect solution. Then you could generate hydrogen, which is nowadays a very good byproduct. It's inexpensive, no reagent waste, all the nice buzzwords I have told you. The problem why this was not done before is if you start with 2 different areoles, then you see a blue and a green one. And if you make a core electrolysis, then you have the blue and the green, and a very tiny amount of the mixed one. The reason of that is that the electrochemical potential is correlated with nucleophilicity, and this is a good selector. And in addition, you make a larger pi system, which is more prone to overoxidation. Therefore, overoxidation is a severe issue, and this was the reason why this was not successful before. But you can do this, and we did it, and I'll show you how you can do this in a scalable way. What we do is that we have a phenol, and we make a phenoxyl radical, still an electrophile. This is trapped by the component, and this has to sneak in selectively, and then you furnish the final product by second oxidation. The important point is you need a helper, and the helper is hexafluoroisopropanol, a very stable, electrochemically very stable alcohol, biologically not so stable, luckily. And the important point is it's an extremely strong hydrogen bonding donor. It means it makes hydrogen bonds to all oxygen, and therefore kind of a specific solvation. It's even not a homogeneous solvent, that means it makes a nano segregation, that makes it very slippy on a nanoscale. That means the viscosity is lower than water, but you have a explicit hydrogen bonding scenery in there. And this is very important because we can exploit it for solvation. That means you have the coupling partner A and B. A is more electron rich, more interesting for the solvent. It's like a rock star being accommodated by groupies and shielded. Therefore, it's electron rich, but not anymore so nucleophilic. The less electron rich one is the more nucleophilic one. And if you oxidize that, you couple these two as long B is there. And by this way, you can soften the shell a little bit by addition of water or methanol. And this is the basic concept behind that. If you have that in your hands, then you can do a co-electrolysis of these two arenes. And you see this selectivity for the biaryl is better than 101. That virtually means in the GC, you only see this biaryl. Then these are isolated yields. You can do this directly here, and you see for prep chemist without pre-functionalization, this is competing less good yield here. And the question is, what is the benefit for the company? Our colleagues from the company, they needed this kind of building block. They made it in a traditional way. And you see, you have to install leaving group, protected, install leaving group protective, and then make a kind of umpolung, do the catalysis and do deprotection. And these are many steps. Even if you can telecope some of them, you can do this by a direct electrolysis, and you save a lot of time and a lot of steps and a lot of chemistry, which saves a lot of money. And therefore, I think this is very convincing. And then you, of course, as an academic person, you sell it in a nice journal, and we call it metal-free and reagent-free cross-coupling. I want to show you also that you can do with the electrode quite a lot. Let's come to cyclopropanes. You find them almost everywhere in drugs. You find them at different applications. Literally 10% of all newly approved drugs have a cyclopropane, which is like a double bond, but cannot metabolize like a double bond. This is the essence behind that. The important thing is now our collaborator had a similar molecule like this one here. This is the first treatment against hepatitis C by Gilead. And our collaborator had this kind of building block several times in his lead structure. And the question was how to make this building block on a 10-ton scale. And the problem is all the features they had in their hands was a kind of a birch reduction. There was a kind of starting material they had to use because they started from hydroxyproline, which was protected, oxidized, olefinated, and the carbene addition to make the cyclopropane. And then you have to remove the bromo or chloro compounds. The bromo was preferentially used because of the situation that this material is easier to purify. However, when they did it, birch reduction was one of the only options, but all problems could happen, ring opening, but also loss of stereochemistry, and the yield was varying. This was the best yield they had, and therefore there was no way. Everyone gave completely different results, and therefore there was no way to get an approval for that. Hydrogenation was a little bit better, but the problem is you had ring opening, and the yield was low, and the purity was not so good as they expected. And then they came in front of my door and said, okay, is there a way to make it electrochemically? And indeed, you can do this electrochemically because you do it under acidic condition. Bach group still survives that stepwise debromination, and then you end with the compound. The initial yield was almost the threshold of their best yield, no racemization or ring opening, but we lost some lead into the compound. What was the reason for that? Well, we had to use high over potential for hydrogen evolution, and therefore only lead was a suitable material. And what is the issue with that? Well, we have to avoid that. Lead is not something you want to have intermediate for pharmaceutical industry. You see, that is partially eaten up during electrolysis, while the leaded bronze we found by screening is almost intact. This is a copper matrix with 7 weight percent of tin and 15 weight percent of lead, and it's similar like pure lead, and it has much more higher stability, which is mechanical but also chemical stability, and it's not so expensive. When we used that, we directly got much higher yield and could optimize this even to quantitative conversion in flow later on. But the important thing is even the trace metal signature was less than 10 ppm, which was exclusively copper. And then the company said, okay, please scale it up. We did in a batch type cell a scale up, which at least brought us a multiple amount of that and almost identical yield. This tells it's a robust process. And after that, we made a flow cell. Just to make it the long story short, this was the smaller one. We pumped it through the bottom to that, and by continuous way, you could make almost quantitative conversion by a single pass electrolysis. This method could be also transferred to late stage functionalization. Cyclosporine A could be a carbene addition, could be easily done, and the cyclic peptide is staying intact for the whole process, even for the electrolysis. And you can do this even on multi-gram scale to get these kind of compounds. The important thing is, and I think this supports the screening power. When we looked at that, we tried to publish it in a good journal. But the problem was at that time, the electroanalytical data looked a little bit shallow. Okay, we were absolutely clear that there are two electrochemical reactions, but it turned out that the leaded bronze is considered as a homogeneous alloy, which is not the case. If you look a little bit more in detail into the system, then you drill holes by mass spectrometry. You have a laser, 500,000 pulses, and then you look what's coming out and the metal composition. And then you have a deviation from the nominal composition, and then you see you have lead-rich and then you have copper-rich areas. And you need the lead-rich for the first bromination and the copper for the second one. And this is, you will not find this by design. It's just by screening you find this in a very good way. And now we come to the last part. Let's call it the dessert that we do a kind of upcycling, and that's where the story should go in. There's something which is known as shuttle chemistry. Not thinking directly about electrochemistry, but by catalysis, this could be done that you transfer two groups from one double bond to another one. Of course, this is reversible, but this would be nice if you can do this with bromine or chlorine without using the direct dehalogens. And if you have something which could be easily stored and which is less toxic and at least less problematic in storage for larger quantities, then you could use that maybe as a chlorinating or a brominating agent. And what is the problem why we used here electrochemistry? This is a collaboration with a colleague from ETH Zurich. He's an expert in shuttle chemistry. He uses usually catalysts, metal catalysts, but the metal catalysts usually do the elimination, better elimination, and therefore you remove here usually one group and one H. And this is the problem, that you do not come to the shuttle of the difunctionalization. You just make HX or HBr or something like this, but you want to go in this way. And by this way, to come in this way, only electrochemistry is helping us. And the good stuff is a paired electrolysis. It's so-called paired consecutive electrolysis. That means we do a cathodic reduction, we liberated the bromide or chloride or whatever, and then we add it analytically to the other double bond in situ in an undivided cell. And this works really nicely. And this is the collaborator Bill Morandi, by the way. And when we did this at simple graphite electrodes, you see it's possible that it can do this on larger scale, but also in the variety of different moieties, which are usually sometimes not compatible with bromine itself. Therefore, the selectivity is definitely given, and you can easily scale it up in a very simple arrangement. For the chlorination, it's a little bit more different, because the liberation of the halogenide is easy reductively, as expected, but the problem is the dechlorination needs manganese catalyst, and this manganese catalyst allows then a relatively selective conversion. Since this is equilibrium, you have to look that one of the intermediates is removed to shift the equilibrium. What could be a really interesting target, and this is, I think, the most interesting target, is there was a time where we made a lot of this lindane or chloropesticides. And these chloropesticides, they're big deposits in Holland, in Germany, in Poland, and in Spain. And because when you make the chlorination of benzene, 80% of the wrong isomers were formed and were just separated off and deposited somewhere. And the important thing is now that you can do this and do the reaction here, and the formation of benzene is promoting that. Then you can, in the scalable manner, you can do this. And importantly, even if you have for example, a 50% lindane in soil, and even a small amount in soil still allows this conversion. I think this is a remediation of contaminated soil, or even some stuff which is deposit is a way to use it. I told you many different stories, but there's not only one simple pathway to make electrosynthesis. There's several ways to tackle things, and I think that the area or the era of electrosynthesis just started. I think there's so many things we can do. We wrote many of review articles in the past, especially some typical areas we do: solvent control and bond-up diamond electrode synthesis. I did nothing of that. I'm very delighted to have my co-workers which brought the ideas to life, which is their really hero effort. And also I'm very thankful to our collaborators because they have expertise we don't have. Well, of course, you need some money for that. I told you some stories which are supported by industry. I think they have high-hanging fruits, and I'm very thankful to them. And of course, some of the stories were also some, Easy Labs is involved, and Easy Labs is a, it's a startup we launched 3 years ago. And if something has to be done which is not possible by the university, then we do it in Easy Labs. And I thank you for your attention, and I'm prepared for questions.
Thank you very much, Dr. Sigrid Waldvogel, and very interesting presentation. And he mentioned the questions. Remember that we are taking the questions at the end of each section. Therefore, we will now hear our third speaker, who I will introduce in just a moment. And after his, we will expect to have questions for our three first speakers from the first segment. You can send them in on the Q&A. Remember, if you downsize your screen from complete screen to a smaller screen, instead of full screen to smaller, you'll find the Q&A there, and that's where you can introduce your question. And please remember to indicate who the question is for. Very well, our next speaker is Mr. Carl Friedrich Hoppe. He is from Evonik Industries. He will be talking about renewable electrical power, which is developed to the energy carrier of the future. The percentage of electrical power generated from renewable sources is constantly increasing. Together with renewable and/or circular feedstocks, this provides an important step towards carbon neutrality, climate and resource protection. Therefore, operation of electrochemical production processes with electrical power from renewable sources will have a trend-setting role in chemical industry. In terms of organic products, the electroorganic synthesis will therefore become an important key technology. The title of his paper is Electrifying Organic Synthesis. So it is my pleasure now to give the floor to Dr. Carl Friedrich Hoppe.
Yeah, thank you for the kind introduction. Good afternoon. My name is Karl Friedrich Hoppe. I'm from the Process Technology Department within the Evonik Operations GmbH and working in the field of electrochemical process technology. In the presentation, I will talk about electrifying organic synthesis with an emphasis on the perspective from industry. At the beginning, I will show some facts and figures about Evonik. Then it will be described how the energy transition promotes the development of electroorganic processes. Aspects of commercial operation are presented in the third part, followed by selected example conversions from the R&D stage. And I will end the presentation with summarizing conclusions. First of all, some information about Evonik. Evonik is one of the world's leading specialty chemicals companies, among the best in class, as you can see from the facts and figures here. We create both profitable and sustainable solutions, making people's lives better day in, day out. Customer proximity and leading market positions give us advantage. No product is so perfect that you can't improve it. Car tires, towels, mattresses, animal food, pills. We don't manufacture these end products, but Evonik is in all of them and in many others as well. Often we contribute just small quantities, but these contributions make the difference because Evonik makes tires more fuel efficient, towels fluffier, mattresses bouncier, animal food healthier, and pills more effective. As mentioned, Evonik is committed to sustainability in our product portfolio, our investments, and our innovation management. And this should take us to the next topic. That is energy transition promoting electroorganic synthesis. As is already known, renewable electrical power is developing to the energy carrier of the future. The percentage of electrical power generated from renewable sources is constantly increasing. This provides an important step towards carbon neutrality, climate and resource protection. Therefore, operation of electrochemical production processes with electrical power from renewable sources will have a trend-setting role in chemical industry. In this context, Evonik faces the challenge and opportunity by using electricity from renewable sources in electrochemical processes for production of chemical specialties. Further considering that the carbon footprint origins 1/3 from energy and 2/3 from raw materials, we arrive at processes like shown here. Used are renewable electricity and feedstocks being renewable, respectively from circular economy. Conversion is carried out electrochemically, producing a raw product that is post-treated, optionally further converted, and finally results in chemical specialties. Another feature of this kind of process is the use of fluctuating and abundant electricity and to store it in the production of chemical specialties. And the overall aim is now to realize such processes. As a large number of renewable and circular organic feedstocks are involved, we arrive next more specifically at the electroorganic synthesis. First, we want to look what happens when electrons are transferred or removed from organic substances by applying an electrical current. These can be uncharged molecules, cations, anions, or radicals, which are listed here on a light gray background. With the reduction, that is transfer of electrons to organic substrates, one arrives at radical anions, radicals, and anions. During the oxidation, that is removal of electrons, one arrives at radical cations, radicals, and cations. In a second step, these intermediates, electrogenerated in this way, react with other components by coupling or nucleophilic, electrophilic, or radical addition. Overall, the electroorganic synthesis enables an easy access to the named intermediates and their preparation on a larger scale. And this is a crucial aspect for the industrial organic electrochemistry. Electroorganic synthesis has the following advantages. The use of electricity enables chemical-free oxidations and reductions. This implies a clear cost advantage since redox chemicals, some of which are quite expensive, can be dispensed with. Looking at the current electroorganic R&D projects within Evonik, one can say this feature is of high relevance. It is, for example, about avoidance of corrosive chemicals or usage of critical metal ions in oxidation reactions. Electroorganic synthesis proceeds under moderate reaction conditions. The reaction rate can be adjusted via the current density. Scale-up takes place via a numbering up of the electrolysis cells and is therefore easy. New reaction paths are made possible. To a large extent, the IP situation is still free, and by use of electricity from renewable sources, it is a sustainable technology, and this aspect has already been described before. We come to the limitations. The use of electrodes basically results in a heterogeneous reaction mechanism, and the electrolysis cells are often process-specific special designs. Reactions always take place at the anode and cathode. That can be an advantage or a limitation. And especially when it's possible to manufacture value-adding products at both anode and cathode, accordingly, the electricity is used quasi twice. The aspect can be clearly assigned to the advantages, and there are already examples of this so-called pair electrosynthesis on a commercial scale. Now we come to aspects of commercial operation. This chart shows a small collection of products that are produced in electroorganic processes on a commercial scale. In each case, the bond formed by electrochemical conversion is marked in red. The so-called Monsanto process for the production of adiponitrile, which we will consider subsequently in more detail, is the largest electroorganic process in terms of capacity. Here is an expanded listing of commercial electroorganic processes. It can be seen that a wide variety of products, for example, alcohols, aldehydes, carboxylic acids, an acetyl, thiol, epoxide, an amino, an azo compound, and fluorinated compounds can be produced on a commercial scale. And here follows a listing of electroorganic process on a pilot scale. If one analyzes the electroorganic, commercial, and pilot processes shown with regard to the types of reaction taking place in them, one finds acetalization, acetoxylation, cleavage, reductive and N-coupling, decarboxylation, dechlorination, epoxidation, fluorination, hydrodemerization, hydrogenation, methoxylation, nitrile reduction, and of course, oxidation and reduction. And it can be concluded from this that for a large number of organic reactions, there is the possibility of carrying out these alternatively electrochemically, whereby the list of reactions mentioned can be even significantly expanded. Overall, this makes electroorganic synthesis particularly attractive, especially in the context of the before mentioned energy transition and the increased use of renewable electricity. Here's a look at the Monsanto process mentioned, in which acrylonitrile is cathodically converted to adiponitrile via hydrodimerization. Side reactions with water, in particular the formation of propionitrile, are initially in principle possible at the cathode. The preferential dimerization is achieved through the use of large unsolvated and surface active conducting Sol cations, as these displace the water from the cathode surface. And the use of these conducting Sol cations was the decisive measure that brought about the breakthrough in the research work for this process. And further here, the note that the electrohydrodimerization is still of interest for synthesis also of other products. In addition, this chart shows qualitatively some process technology aspects for the development towards an industrial electroorganic process. Not complete and in detail rather more complex. It is, of course, under the aspect to be competitive with a conventional organic process. First of all, R&D efforts should be directed towards the production of valuable products at both anode and cathode. The decisive parameters for the R&D stage are both high current efficiency and high yield of the anode and cathode product. Here, it should be once again referred to the Monsanto process. During its R&D stage, current efficiency and yields quickly went up to practically 100% after using the before mentioned unsolvated and surface active conducting Sol cations. A broad current density range is beneficial for easy application and makes the system robust towards fluctuation in electricity consumption and reaction parameters. But there are substrates being sensitive towards higher current densities, and then therefore still only a few electroorganic processes are carried out at high current densities. For example, the Kolbe electrolysis and the Monsanto process. Therefore, high current density, of course, primarily aims at reducing the investment costs. Another parameter is a low voltage for low heat generation and a low specific energy consumptions. Electrodes and membranes should be stable for a longer operating time span. Electrode leaching, deactivation, and blocking by formation of deposits should be avoided. First steps in this direction are, for example, the use of boron-doped diamond electrodes. The electrode must meet, amongst others, the requirements conductivity, stability for the electrochemically active components, low vapor pressure, good transport properties, and high heat capacity for the electrolyte if it is also a heat transfer agent. Design objectives of cells are, for example, homogeneous current density distribution, low voltage drop, high mass transfer rates, ease of electrodes, respectively membranes replacement, and bipolar series arrangement, all at the lowest possible construction costs. Reagent waste should be largely avoidable as electrons are used in place of redox chemicals. In continuously operated cells, the conversion is incomplete. Therefore, good separation of the product from electrolyte, intermediate products, and feed components is necessary. In the electrolyte recycle, an undesired accumulation of components, especially impurities, must be avoided. And in the end, the remark, the technical scope and investment, respectively, operating costs of the electrolysis unit will be only a part of the corresponding scope and costs of the overall production plant, which decide, of course, about the profitability of the total production process. Now we come to a number of electroorganic syntheses which were investigated within Evonik or may be of potential interest or currently discussed in the literature. Since the electrification of chemical processes is being of increasing interest now, these syntheses appear in a new light. Their feasibility and economic efficiency are partly being re-examined. I would like to start with the diverse uses of nickel hydroxide electrodes for chemical-free oxidations. These enable, amongst others, the production of carboxylic acids and ketones from primary and secondary alcohols. Individual hydroxyl groups can be oxidized with high selectivity in larger aliphatic molecular structures. Hydroxyl groups of beta-hydroxyethyl ammonium compounds can be oxidized to the corresponding glycine derivatives. Oxidative ring openings take place at elevated temperatures. This is of interest since corresponding reactions are currently carried out using nitric acid. In contrast, the reaction with nickel electrodes takes place under alkaline, non-corrosive conditions. And as you of course know, using nickel hydroxide electrodes in electrochemical synthesis provides also a link to the content of the LIBERATE project. This figure shows an experimental setup applied for the use of nickel hydroxide electrode in electrosynthesis. A so-called Swiss roll cell is utilized here, in which a nickel mesh anode and stainless steel mesh cathode are rolled up on top of each other, separated by a polypropylene mesh. The reaction solution is pumped continuously through the cell. In many cases, the challenge is the low solubility of the organic feedstock in the alkaline phase. An improvement was achieved in this project by replacing a gear pump with a peripheral pump, which disperses the organic phase better in the alkaline phase. Alternatively, or additionally, co-solvents such as tert-butanol or surfactant components can be used for this purpose. The oxidation of diacetone L-sorbose to diacetone 2-keto-L-gulonic acid, which is an intermediate stage in vitamin C production, shows that the usage of nickel hydroxide electrodes is not limited to research. After laboratory development and piloting, the DAG production was transferred to a commercial scale with a capacity of over 2 tons per day. The photograph on the right shows the commercially used large-scale Swiss roll cell, several of which are connected in a cascade. We come now to the electrochemical carboxylation. This makes it possible to convert monoolefins and 1,3-butadiene to mono and decarboxylic acids. Furthermore, aliphatic conjugated dienes and conjugated fatty acids can be used for carboxylation. Within Evonik in particular, the carboxylation of aldehydes to alpha-hydroxy carboxylic acids has been intensively investigated. A corresponding experimental setup for screening tests is shown on the right. Analogically, for example, magnesium consumable electrodes or inert electrodes are used. The carboxylation of the aldehyde takes place at the cathode, for which doped diamond film is preferably utilized. In the case of olefin carboxylation, for example, nickel or graphite is chosen as cathode material. From the reaction examples, it can be seen that the electrochemical carboxylation enables a one-step conversion from a commodity to a specialty chemical, particularly in the direct synthesis of decarboxylic acids, which are used, amongst others, in the production of high-performance polymers and in further high-performance applications. With regard to the electrification of organic synthesis, we have so far only considered processes that consume electricity, meaning electrolysis processes. In the case of oxidation reactions, one can now consider not using conventionally the enthalpy of reaction in the form of heat, but rather the free enthalpy of reaction while generating higher quality electrical current. It means that the oxidative conversion is carried out in a fuel cell reactor. This is shown in the figure here using the example of the hydrogen cyanide production taking place at high temperature. The starting materials, methane and ammonia, are supplied on the anode side and oxygen on the cathode side, which migrates through a membrane as an oxide anion. At the same time, electrical energy is generated by the flow of current via an external conductor, which can be utilized externally by consumers. And estimates based on thermodynamic data have shown that conventional oxidation results in a credit of 166 euro per ton hydrogen cyanide from steam production, while fusel oxidation results in a credit of 354 euro per ton hydrogen cyanide from electricity generated. So an economic advantage of electricity compared to the presently applied steam production. And one more addition, this exploratory concept for electrification can also be transferred to other oxidation reactions of organic compounds. The last topic takes up a completely different aspect of the interaction between electrochemistry and organic synthesis. It is about the so-called electrochemical promotion of catalysis, abbreviated as EPOC or earlier NEMCA effect. This allows the rate and selectivity of heterogeneous catalytic gas phase reactions to be drastically increased in some cases. For illustration, the experimental setup of work on EPOC is shown here. The epoxidation of ethylene to ethylene oxide is investigated here using porous silver, which functions at the same time as a catalyst material and as an electrode. Underneath the silver anode, an oxide conducting solid electrolyte is installed, followed by a porous silver cathode. Smallest amounts of oxide ions are conducted through the solid electrolyte to the upper silver layer by means of an electrical current. And now one observes that the actual reaction of ethylene with the oxygen in the gas space to form ethylene oxide takes place with an increased reaction rate and selectivity. In other words, the ratio of reaction rate with electropromotion and reaction rate without electropromotion attains values greater than 1. Specifically in publication D, a maximum value of 4.6 was achieved based on the ethylene oxide synthesis. In other reactions, the ratio even goes into the double-digit range. EPOC can be transferred to further reactions, such as methanation of carbon dioxide, oxidative methane coupling, as well as dehydrogenation, and particularly interesting for Evonik, partial oxidation of C2 to C4 hydrocarbons. Final point are now the conclusions. Regarding the electrification of organic synthesis, respectively electroorganic chemistry, I see 3 main aspects. The R&D hurdle to get to a commercial process is high. In my opinion, the main reason is the interdisciplinary nature of the technology. But it is possible to take this hurdle as the commercial processes showed at the beginning, and then you have achieved an exclusive, unique position. Electroorganic chemistry is a powerful and efficient technology for the production of, in particular, specialty chemicals using an alternative route to conventional synthesis. This was made clear by means of examples in this presentation. And finally, it supports the transformation to sustainable chemical processes through the use of electricity generated from renewable sources, avoidance of carbon dioxide emissions, and in some cases, as we have seen, even through the consumption of carbon dioxide. That brings me to the end of the speech. I thank for your kind attention, and I'm pleased to answer your questions.
Sí, garrafos de la casa. Thank you very much, Carl Friedrich Hoppe, for that very interesting presentation. And yes, as we said, we have heard the three speakers of this first session, and now it's time for questions and answers. Unfortunately, Siegfried has had to go to another commitment and will not be able to join us, but we're going to take questions for Angels and Carl. So let me see, I've been given some, let me remind you, by the way, that you still have time to ask questions using the Q&A, both for this session as well as the other two sessions that will be coming up shortly. So please feel free to introduce your questions, say who they're for, and if we're not able to cover the questions because of time, we will make sure that your questions are answered on email, that they respond to them. So please join in and participate, which is an important part of any webinar. Now, let's see some questions. I'm going to begin. I've been given some questions for Angels. Angels, the first question, how does P4Planet roadmap build on Spire projects results like LIBERATE? I believe your microphone.
Sorry, now I was unmuted. Sorry about that. So let me start again. Thank you for this question. I think I really like this question because normally what we do is we do a yearly progress monitoring report on the results of the projects. And then also out of this report, then we do an analysis, and sometimes we do extra surveys to the projects so that we understand how are they progressing. And then also we trust also in our members that are part of the projects and part of our working groups to alert us, hey, we cannot go on that direction because it's already been done, so we don't need to repeat it, or because it's proven that it's not the right direction, it's not working, and it's better to go for this or this other direction. So for example, to make you a very clear example, on Spire was building very, very importantly on industrial symbiosis. But then an important point also were some tools for the identification of this information, the data for industrial symbiosis. And then in the course of Aspire 2020, we moved to higher projects, more ambitions, and we moved in our roadmap from the concept of industrial symbiosis to the concept of industrial urban symbiosis. And then we move further in our roadmap also to the concept of the hubs for circularity to have a look at this systemic perspective. So this is a very clear example of how we built on the results of our projects, so that the calls really, every new call moves forward in the advancement towards the achievement of the objectives of the partnership.
Thank you very much, Angels. Perfect. Now let me ask another question. In this case, it's for Carl Friedrich. The question is, what determines the use of an undivided cell or a divided cell in the electrosynthesis?
Thanks for the question. Sorry, I have to turn this down. Yeah, an undivided cell is, of course, always desired because the construction costs are low and the operation is simple, but it cannot be realized in all cases. A precondition of electrolysis in an undivided cell is that disadvantageous reactions products at the counter electrode can be avoided. Also, for example, this can be done for example by selection of the electrode material or the electrolyte composition. But in many cases, it's likely to be impossible to prevent unwanted reactions at the counter electrode, and then you have to use separation between anolyte and catholyte. And basically, there are two different types of cell separators available. So on the one side, the porous separator with unselective ion transport and ion exchange membranes, which supports selective transport of cations and ions.
All right. Thank you, Carl. Let's go back now to Angels. The question is, the co-programmed partnerships like Processes for Planet have a new scope under Horizon Europe. Why does this simplify for Aspire community?
Well, I'm not sure it simplifies, but it definitely adds new benefits to the community. So in the past, under Horizon 2020, Aspire Partnership worked exclusively on the topics of Horizon 2020 that were labeled Aspire specifically. So that was our major contribution. Now, with a new setup of the co-programmed partnerships like Processes for Planet under Horizon Europe, the scope is a bit wider. So, for example, before we supported the projects, but we could not support them much farther from TRL 7, that was the level up to which Horizon 2020 supported the projects. Now we can support our projects and our members to move forward towards TRL 9. Of course, for that, we really need that the projects, the new projects, are very, very ambitious so that they can really deliver. The impact panel will not consider, for example, projects which really will not be able to deliver the targets of the European Green Deal. So if a project says, no, I'm going to reduce 40% emissions by 2050, okay, that's not what the European Union is searching, right? So we really need, and I would like to encourage everybody to present very ambitious projects. But it's not only projects that are linked to the funding. So companies like Evonik or other companies which are members of Aspire, they can really present other initiatives to see how they can be further supported beyond Horizon Europe by the European Investment Bank or by other sources of funding or financing, sustainable financing, so that they can really get to TRL 9 and then we can get to the phase of deployment. So for me, that is already a very, very important advancement.
Thank you. Thank you very much, Angels. And I have to apologize because it wasn't simplify. The word this, imply, were very close, and I saw simply, and I turned it into simplify. So, but your answer was perfect. Thank you very much. Let's go to another question for Carl Friedrich. What are the characteristics of batch operation and flow-through cells in the electro-organic synthesis?
Okay. The very basically question, they are on even on a commercial scale, both types are operating. In fact, the batch operation is the simplest way of electrolysis and mostly applied to electroorganic synthesis. So here the reactant concentrations, of course, decreases with rising degree of conversion. Question is to maintain a high level of selectivity, of course, and this can be done by potentiostatic cell operation. Although the current will go down, the limiting current density, so by a potentiostatic operation it can be maintained. And the big advantage of batch operation is, of course, that much information can be retrieved from the batch operation, concentration curves, kinetics, and so on. And on the other side, in the flow-through cell with steady state operation, one realizes, of course, constant process conditions of concentrations, other parameters. But the disadvantage or feature is with that to be considered that we need additional equipment pumps, for example, and the continuous operation will be applied if optimal electrolysis conditions are achieved with very well-defined process conditions. No? Or if, example, cell components have to be operated at constant concentration, for example, this is the case for ion exchange membranes. Fact is, in the end, the large-scale industrial in the large-scale industrial cells are operated normally under steady state conditions, so continuously.
Well, thank you very much, Carl. We're going to let it go here. We're running out of time for our questions and answers. I would like to thank both of you for your presentations and for answering your questions. And one of the questions that has come up, but that wasn't for any of our speakers, is if this recording will be available. And yes, I would like to inform you that once we have completed our webinar, the webinar will be up and available on the same platform, the same website where you logged in. So you can go there, and of course on the social media of Liberate, Perform, Inspire, you will also have links or it will be right there for you to see the entire webinar. So if you missed anything or you have to miss something because you have an urgent meeting or a phone call, you can go back later where you signed up for this and watch the entire thing or watch the part that you missed. So once again, thank you to our speakers from our first session, which was the plenary session. And now we move on to our second session. Well, it's actually titled Session 1, but it is our second segment of the day. It's titled Bio-based Feedstocks. And we are going to hear from Mr. Bernd Witkens. He is Senior Advisor at SINTEF. Briefly, LIBERATE represents a powerhouse consortium, including 3 major multinational chemical companies, SMEs, 4 internationally regarded research and technology organizations, and leading European universities. By overcoming the technical developments, pilot line scale-up, and commercial exploitation barriers of the next generation of biorefineries, LIBERATE is working to deliver a pilot-scale electrochemical plant to demonstrate the commercial opportunities of converting low-cost lignin feedstocks into high-value biosustainable chemicals. So let's hear now from Bernd Witkens. That will be, well, the title of his talk is Lignin Biorefinery Approach Using Electrochemical Flow Project.
Thank you for the introduction. My name is Bernd Witkens. I'm working for SINTEF in Norway, and I'm involved in the project LIBERATE, lignin biorefinery approach for using electrochemical flow. Let's see, that does not work. Okay, the concept of LIBERATE is to convert low value lignin feedstock into high value chemicals. And the objective of LIBERATE is basically building a pilot plant which do that job. Lignin, several different types of lignins available. We are concentrating on cleft lignin and organosolv lignin and their conversion. The challenge, as we in previous presentation heard, is that cracking hydrolysis gives you quite a number of different products. We are applying an electrochemical oxidation towards aromatic compounds. The LIBERATE process itself, we have 3 different feedstocks. Kraft lignin, the intention is to go towards vanillin, organosolv lignin to mixed phenolic derivatives, and also cyclohexanols towards 3-propyl-adipic acids, which can then be later on used. Yes?
Bernd, I'm sorry, I hate to interrupt you, but your presentation is not in full screen, and it would be much better if it were. If you go to the top, you'll see that there are 3 things. The one in the middle, if you click on that, you will see the first option. Do you see display settings? Okay, go to display settings and click on display settings. There you are. And the first option, hit the first option, and that should do it. The first option on the top. There you go. That's perfect. Thank you very much. And sorry to have interrupted.
Okay, now now it's the other way around on my screen. Okay, sorry. But okay. So basically we are producing vanillin as a product and platform chemicals toward antioxidants, phenol, formaldehyde adhesive towards caprolactones and aromatic aldehydes or polyamide and unsaturated polyester resins. The project is part of SPIRE. We have a total budget in the order of 10.05 million euro with 8.8 million euros from the European from SPIRE, and we will finalize the project by end of 2022. And the partners are Perstorp in Sweden, Evonik, Gondias and Fraunhofer in Germany, Shimar and Megara Resins in Greece, and Auxeris, Enso, Leitat, Idenia, and University of Alicante from Spain. Then we have TNO and NX Filtration from the Netherlands, and Gate to Growth in Denmark. So it's a nicely distributed consortium. The main objective, we would like to get 7% yield of vanillin from kraft lignin towards 35% of phenolic derivatives from organosolv lignin, and convert 80% of our cyclohexanol into propylipidic acid. So basically biorefinery process where we look into an improvement both with respect to energy efficiency and resource efficiency, and also reduce the CO2 footprint of the products. But most important, we intend to use intermittent renewable energy without losing efficiency of the process. So the timeline, we are now a little bit longer than halfway into the project. We are more or less on track, so COVID has quite some influence. And yeah, things are going quite well. The value chain of the project is we have our starting materials, then the electrochemical process, our flow system where we convert it, and then we build that into a system demonstrator, because until early 2020, only those processes have only been run in batch process. We try to build a continuous pilot system, and then of course a validation of the system, and then a market assessment. The first part is basically we need to set the stage, and this is get all the information we had from the process, from the individual batch process, develop flowsheet alternatives, and evaluate these and see if they're valuable. Then modeling the process units, integrate these units, and then perform a basic design and engineering of the process. From the starting material, we also try to utilize the feedstock directly. For example, we used organosolv lignin, which is of a more better quality than kraft lignin, and we use it directly for replacing phenols in phenol formaldehyde resins. That is successfully performed, and there will be some follow-up experiments to increase the replacement amount. The electrochemical process, the flow cell which Siegfried actually previously showed is scaled up with about a factor of 6. The design is slightly changed, and then the reactor is produced through additive manufacturing and chemical vapor deposition. And in the tests we have run up to now is show that the electrodes are in operation for more or less 100 hours of operation without degeneration. And now we are implementing the reactor system into our pilot plant. The Bodic reduction, when we started actually the project, it was mentioned that we had to operate it at sub-zero temperatures, which is a little bit of a hassle. So during the recent times, we managed to increase the operation range up to 10 degrees, which is much easier to operate because we can use conventionally cooling sources. On the right, you see a picture of the lignin dissolved in water before and after the electrolysis. So the initial results we have now is that we get a yield of up to 6 weight% from vanillin from kraft lignin, which is about 3 times higher than the commercial process, and about 91% effectiveness with relation to the energy consumption. For the propylapidic acid, we are roughly at 60% of the theoretical yield. So that means we have quite some way to go. But both reactions are transferred now from the laboratory to the pilot, means larger electrodes. And also we have established larger systems without significantly changes with respect to yields or the selectivity of the reactions. Downstream processing, we have tested several single module filtration systems where we get selectivities up to 85% and 75% different phenolic compounds. The challenge is with the chosen membranes is that we have relatively high dilution rates. That means we add even more water to the process than we already have. For the pilot system, we left the membrane path we developed in the start and go towards an ion exchange system, where we basically can recover about 100% of the monoaromatic phenols from the process. So it's considerably more efficient, and probably it will be more economic, but we don't know that yet. The pilot system, here you see a few pictures from the lab. On the left-hand side is the reactor. It's basically a plug flow reactor where we can control temperature and residence time in the reactor by increasing or decreasing the number of modules we're passing through, a feedstock preparation, and then electrochemical reactor. We have performed design of experiments to optimize the reactor conditions. And this is work which is still ongoing. We have to find out how to, for example, reduce the amount of sodium hydroxide in the system, or how can we increase the amount of lignin in the system. Both has quite dramatic effects on the operation costs of the system. The downstream system I mentioned, for the vanillin extraction, we use an ion exchange system. For the higher molecular weight systems like lignin derivatives, we're actually now just looking in how to recover or remove the water from the process flow, because we can deliver some of the derivatives as they are. We just have to reduce the water content. Then the validation of the system, we have spent quite a lot of time to define the base case. So what is the LIBERATE process itself, and coupling it to upstream and downstream processes. And then we started to perform a technical economical evaluation and a life cycle assessment. So we had to identify the required data, perform an efficient way of an information exchange between the different disciplines in this project, like technical economic evaluation, LCA, process design. So what we did, we built a process database where all the data which are relevant for the project are accumulated, and we can use all these data within all the parts of the project. The technical economic evaluation, I mentioned shortly earlier that we have relatively low concentrations of feedstocks in our system. We work generally with 3 to 5% lignin. So that means we have very high water amount in the system circulating, and that has a very substantial influence on the separation cost, because the separation costs are currently the dominating cost of the process, and we need to find out how to reduce these. The LCA analysis, we defined two different battery limits for this analysis. One is a cradle to the grave approach, where we also include, for example, the resource extraction, the production of the lignin and the production of a product itself and the component use towards end of life, or more a gate-to-gate perspective. The reason for the second one is basically then we can compare different scenarios with each other, because in some of the work we see that the impact of the feedstock production is much higher than the conversion of the feedstock to the product itself, and that makes it hard to compare different processes. The other input is the renewable energy supply. Then we need to use to calculate our electricity consumption and where the electricity actually comes from, and the chemicals, etc. So the LCA methodology is basically divided between the mass flow allocation and the economic allocations of the system. Some conclusions. We have designed a continuous pilot plant, including the downstream process system, based from data which are generated from batch processes. We are working on the commissioning and also run some of the initial experiments, which is everyone who tried to build a pilot plant knows exactly what we're going through. So it's the up and down of this lab work. We perform currently some research tasks in parallel. We need to increase even more our understanding of the oxidative reactions, and that is to design our experiments better and maximize production. And then we need to look in how far we can go by replacing phenols in resins with the products we are producing. So the plans for the near future is we want to start the continuous operation of the pilot plant by the third quarter in 2021. And then on the theoretical side, we still have to perform a scale-up, which is valid for an industrial implementation. And then in turn, we have to perform a technical and economical evaluation and the life cycle assessment of the entire system. That concludes my talk, and I will be happy to answer any of your questions.
Thank you very much, Bernd. And we will get to those questions at the end after we hear the three speakers. As you know, we will take all the questions that come in through our question and answer feature of the website platform that we're using. So thank you very much. And now let's move on to our next speaker. Our next speaker will be talking about PERFORM, which is Power Platform Together. And he's going to give us a project overview, a general overview of the PERFORM project, looking at key technologies developed and the technical developments achieved so far. So we will be hearing from Mr. Roman Latsuzbaya, who is a scientist at TNO. Mr. Latsuzbaya, the floor is yours. Muted. Uh-oh. ¿Se lo digo? Roman, can you hear me? Sorry, you're muted. We haven't heard what you said so far. So please go ahead and unmute. And then you can put your screen in full screen again, because we don't want to miss a word of what you have to say. So I see you're still muted. Okay. You were close. Let's see if... Let's see if we can solve the problem here. And there you are. You're unmuted. Can we hear you? Can you try, please, just to...
Hi, everyone.
Perfect.
I think you can hear. Apologies for the...
Thank you. Perfect.
Delay. So good afternoon, everyone. I would like to present today overview of PERFORM project, PERFORM or Power Platform European Union supported project. The project is supported by European Union Horizon 2020 research initiative, and it's a 4-year funding. The project started in January 2019 and it's gonna be ended in June 2023. We have a small delay due to COVID pandemic. So overall objective of the project is to demonstrate feasibility of the production of electrochemical production of chemicals, bio-based chemicals. So the main goal is development and construction of a highly versatile and modular electrochemical production system, a power platform system with a productivity of roughly 250 grams per hour and a surface area of electrochemical electrodes up to 1 meter square. The goal of this project also to demonstrate a flexibility of this power platform, and for that case we will have two showcases, two reaction, and we are working with two cases and also variable electricity input. And finally, the goal of the project is also the dissemination and exploitation of the innovations achieved in this project, as well as the final power platform, which will be an open access infrastructure available afterwards to other research players to demonstrate the electrochemical production processes. So the motivation of the PERFORM project. So our society is facing grand challenge, becoming carbon neutral by 2050. And in order to achieve this carbon neutrality, we need to decarbonize our energy system, but at the same time, we need to make sure that our chemical industry also recarbonized with renewable feedstocks such as biomass, carbon dioxide, or other waste streams. And in this project in PERFORM, we target these two global trends, energy transition and electrification, as well as shift towards bio-based feedstocks. So the project concept, in this project, we are aiming development of highly efficient and integrated electrochemical system for transformation of bio-based chemicals. And the starting point of the project is actually TRL2-free, the electrochemical reactions. And at the end of the project, we are bringing this reaction to TRL5-6. So the focus is on renewable feedstock, as I mentioned, variable electricity input, renewable electricity input to produce high value-added chemicals. And in this project, we are going to develop electrochemical reactor as well as downstream processing technologies related to the products we are working on. So if you look at the main activities in this project, so we are working on a feedstock platform in innovation and analysis. We are developing electrode materials for an efficient reaction. We are developing system platform, which means the electrochemical reactors and downstream processing units. And in the final steps, we are going to demonstrate a continuous electrochemical production with the target performance, which will allow us in the final step to assess the electrochemical production of our target molecules, and also to show the potential, technical but also economical potential of this transformation. as well as the reduction in emissions. So the key innovations actually which we are working in this project is paired electrochemical system. So the focus here is to make our electrochemical processes more efficient. So an anode and a cathode we would like to have to produce useful chemicals. Additionally, we are gonna, in order to achieve efficient electrochemical transformation, we need to scale up we need to develop and scale up novel electrode materials. In these electrode materials, also very important to achieve sufficient productivities at a good performance. For that, we need to make sure that we are going to work on electrochemical process intensification. And finally, very important to develop an integrated electrochemical process. So looking at electrochemical reactor as well as downstream processing of the final products. So to showcase, in this project, we selected 2 showcases. So in the first line, we look at the oxidation of furfural to maleic acid on the anode of the electrochemical cell, whereas the cathode, we look at the reduction of limonenic acid to valeric acid. This is the first line of the project, which we are working on. In the second showcase, we are working on a glucose to adipic acid conversion. It's a tandem electrochemical system by glucaric acid. So the focus, as I mentioned, is indeed on bio-based production of bio-based chemicals for the applications such as polymers, plastic, synthetic lubricants, and others. So these are quite important chemical building blocks in chemical industry. And in this consortium, we have also end users which are testing these final products and helping us to make sure that we deliver good quality products. So in general, we have quite a strong international consortium. We have 11 partners from 7 countries. We have from Italy, we have INSTM together with Vito and Avantium, which are looking at the catalyst development and electrode development. Vito together with TNO and Hisitech looking at the reactor and downstream processing development. University of Hohenheim is helping with the process assessment and LCA. We have end users in this project, as I mentioned. We have Ava Biochem, which is helping us with the techno-economic assessment of these 2 different reaction lines. And finally, we have Sustainable Innovation, which is helping us with exploitation and dissemination of the results. So if you look at the main activities of the project, we have 3 phases in this project. We start with the first phase, which is analysis and innovation phase. In this phase, we look at the feedstock analysis, at electrode development, and we have hardware development, which means development of electrochemical reactors, as well as downstream processing units. Additionally, we also look at the materials assessment and we do market analysis. And in the first phase of the project, we look at electrochemical conversion in a scale few centimeters square up to 100 centimeters square. Currently, we are completing phase 2 of the project, where already we designed the process, overall process for both line. We designed electrochemical reactor, we constructed and built it. And at this scale, already at 1000 centimeters square, we are able to produce the products in a scale roughly 20-30 grams per hour. Currently, we are busy also to translate this into a power platform, into the demonstration platform. So we are constructing the demonstration unit, which should be ready next year, where we are going to perform demonstration of our reactions continuously for more than 200 hours and demonstrate technical but also economical feasibility of these conversion routes. So let's start from the first activity, which we are busy. In feedstock analysis, basically, there are 2 main activities. We develop analytical methods to characterize the feedstock, but also we look at the pre-treatment of feedstock to make sure that there are no detrimental contaminants present for electrochemical reaction. In this part of the project, Avantium is busy, especially focused on the feedstock from the down technology, glucose, to make sure we have a good feedstock for electrochemical reaction, electrochemical conversion. At the same time, we also have supply from the partners of feedstock such as furfural and limonenic acid. The core of the project, of course, it's the catalyst. So the objective here is to develop electrochemical system, the catalysts, which are selective and efficient with selectivities above 80% and Faraday efficiencies above 80% at current densities 100 more milliampere per square centimeter. More importantly, the focus is development of stable electrode materials. So far, our partners here at AnaSTM, together with Avantium and Vito, they already developed various number actually of the active catalyst materials on different supports such as carbon nanotubes, titanium nanotubes. We demonstrated that these catalyst materials are active and stable. We obtained selectivities and Faraday efficiencies between 50 to 90% for maleic, valeric, and glucaric acids. Adipic acid is still a bit challenging, but we are working on it. Currently, we are also busy into building electrodes of 1,000 centimeters square into our pilot reactor in order to achieve target productivities. So currently, reactions are being optimized at lab scale, and we are building manufacturing large-scale reactors here. So another important activity in this project is actually reactor scale-up. At the beginning of the project 2 years ago, 2.5 years ago, we started with reactions at a scale few centimeters square. Then we scaled it up to 100 centimeters square reactor and a system around it. And finally, currently, we have a designed and constructed reactor, which is 1,000 centimeters square with productivities, tens of grams of products per hour. Currently, we are optimizing this reactor, and we are also designing a pilot stack reactor. So in the pilot, we will have the total surface area up to 1 meter square, and there we will have several cells in a stack reactor. Here, TNO, together with Hisitec, Vito, and Avantium, designing this reactor, and Hisitec, our partner, constructed the reactor and will help us to construct the pilot. Very important, and it goes hand in hand with the reaction development, is actually process development. But in reactor development activities, it's important to match the process development and reaction. Here we have target energy efficiencies above 55% and decreased operational and capital investment by 25%. One of the important aspects of our reactor that we designed a flexible electrochemical reactor where we can vary inter-electrode distance, and we can also test different electrode materials such as plate, mesh, and metal forms, and etc. So the final pilot platform will allow test other reaction types apart from the reactions which are developed in this project. In this activity, in reactor development activity, we started with the conceptual design of reactor. We did some modeling studies where we looked at the aspect ratio of the reactor, we looked at the dimensions of the reactor, as well as use of different electrode types such as plate up electrodes or metal foam electrodes, and then to arrive to a final design of the electrochemical reactor. And as I mentioned, currently we are optimizing this reactor. In parallel, we are also busy with the process development. As Professor Waldvogel mentioned today, the downstream processing can be a killer of the process, overall process. So in order to avoid problems in this project in future, we are developing parallel and optimizing the reaction as well as downstream processing of the products. The objective for us in this project to achieve recovery of products with 90% yield and purity of 95%. Most of our partners in this project are busy with this activity. The partners developing downstream processing technologies as well as the end users which are advising us with their experience. The specific challenge actually with electrochemical conversions that is very often you work with a low concentration of products. So that very often requires pre-concentration step, selective and efficient extraction, and importantly, electrolyte recycling. So in this activity, we looked at the recovery and purification of the products, but also electrolyte recycling for both lines of the project. So the current status of the process development activities is that we actually designed and optimized the downstream processing technologies for both lines in lab scale. We looked at many different downstream processing technologies, such as extraction, distillation, electrodialysis, nanofiltration, crystallization, and many more. At the end, we designed overall the process, and based on the overall process, we selected suitable pilot units, and currently we are busy with acquisition of different pilot units, which I mentioned in this list. Here we have images of the pilot units which we acquire, and some of them we actually built already, like a crystallization unit. So we are in process of actually acquiring all these pilot units and constructing the final demonstration unit, which will be ready in the beginning of 2022, and we will be ready for continuous demonstration. In parallel, from the beginning till the end of the project, we are guided by our partners, University of Hohenheim and our Biochem, which are looking at the life cycle assessment, impact analysis, but also helping us to optimize the process in order to achieve increased process efficiency, increased resource efficiency by 35%, and halving the emissions of CO2 compared to benchmark, compared to standard industrial process. At the same time, in this activity, we also look at the intermittent electricity supply to understand how can we make this process even more economically feasible. So in this activity, University of Hohenheim together with our Biochem are busy, but also end user are helping and they're doing application testings of the molecules which we are developing here, maleic acid, valeric acid, glycolic acid, and adipic acid. Of course, it's very important also to make sure that the process is techno-economically feasible. Here, our partners, our Biochem and University of Hohenheim, from the beginning of the project, they provide us techno-economic assessment of both showcases, but also at the end of the project, they will provide final techno-economic assessment and benchmarking after we obtain the demonstration results. Already some preliminary economics show potential positive business cases if the targets of the projects are reached. So this brings me to summary of my presentation. So far in this project, in the first 2.5 years, we already demonstrated a selective and efficient electrochemical conversion, but also integrated downstream processing in a lab scale. Based on this result, we designed the whole process for both lines, for maleic, valeric, glycolic, and adipic acids. We will construct the power platform, which will be TRL-56 power platform in the beginning of 2022. Hopefully everything will go well and we will finish with this demonstration in 2023. And we will build this flexible electrochemical reactor stack platform where you can test different electrochemical production methods with different electrodes, which also have a modular downstream processing technologies which are quite general and applicable to other electrochemical processes. So the location of the pilot is not decided yet, but to be decided soon. So at the end, I would like to thank all the participants of the project, of the consortium for this incredible work which we've been doing so far. And I'm actually looking forward to seeing everyone face to face, and hopefully we can do that soon. And thanks, audience, for your attention.
And thank you, Roman, for that very interesting explanation of the PERFORM project. Now, as I keep repeating, the questions will be taken at the end of this segment. So we have one more speaker, who is Mr. Bart van den Bosch. He is an R&D chemist at Avantium, R&D in chemistry at Avantium, and he will be talking to us about anode materials for paired electrosynthesis. Very quickly, electrolysis can provide more sustainable and thus more competitive alternatives to petro-based processes. At Avantium, a multidisciplinary team works on the development of sustainable new electrocatalytic processes with potential large-scale application. Dr. Bart van den Bosch is developing processes in which CO2 reduction reactions are coupled with oxidative processes that yield valuable compounds. By pairing valuable reduction and oxidation reactions in a single reactor, the expenses associated with electrosynthesis can be substantially lowered. So, Dr. van den Bosch, if you'd like to tell us about that, the floor is yours.
So thank you very much for this introduction. So indeed, I'm a scientist at the electrochemistry department of Avantium, and I will talk about anodes for paired electrolysis. So as Roman already said, in PERFORM, we are doing 2 reaction lines that both have a paired electrolysis process. So we have the oxidation of furfural to maleic acid, and this is paired with the reduction of levulinic acid to valeric acid. And in the second reaction line, we have the oxidation of glucose to glucaric acid. And this glucaric acid is then input for the cathodic process, where it's being reduced to adipic acid. So why are we working on these reactions? All these 3 compounds are commodity chemicals. And currently, they are made in industrial processes from fossil-based resources. So maleic acid is obtained by the oxidation of benzene or butane. Valeric acid is obtained from hydroformylation of butene. And adipic acid is made from these 2 compounds, which is also mentioned, or which is also called Ka oil. Of course, we want to go to a bio-based economy where the fossil-based feedstocks are replaced with bio-based feedstocks. And I heard this quote once, it said, sugar is the new oil. And if you look at the PERFORM technology, where these compounds come from, they can all be obtained starting from carbohydrates or sugars. So furfural can be obtained from xylose. Levulinic acid can be obtained from fructose or glucose. And as already mentioned before, the glucose for reaction line 2 is made by Avantium's Dawn process. In this process, non-food biomass is hydrolyzed to achieve glucose. So basically, sugar is the new oil in the sense that this is also a source of carbons, but this is a more sustainable source of carbons. And you can think of routes to obtain the compounds that you normally get from oil. You can also think of routes to obtain them from sugars. Avantium is involved in 3 steps in the process. First of all, as we mentioned, the Dawn process, where glucose is obtained from non-food biomass. Then Avantium is also involved with our polymer department, where we test the feasibility of making bio-based polymers from the adipic acid that is being produced in the project itself. My involvement is mostly in the oxidation reaction of furfural to maleic acid. So this is also the process about which I will talk in this presentation. and with a focus on how to pair these two reactions. What is important for pairing reactions? But first of all, why is it important to pair these reactions? So if you look at a single reaction, or the reduction reaction alone, and you look at the input that's required to make 1 ton of valeric acid. So you need 1.13 ton of levulinic acid. And you can see that the electricity costs are a substantial part of the manufacturing cost. So if you assume a cell potential of 3 volts and a Faraday yield of 100%, and an electricity price of 13 cents per kilowatt hour, the electricity cost for the conversion is 204 euros per ton of valeric acid. Here we do the oxidation of water, which is a non-valuable reaction, and also it generally requires quite a high overpotential. If you can replace the water oxidation by the oxidation of furfural, you can have valuable products on both sides of the electrochemical cell. So a reduction reaction alone and an oxidation reaction alone may not be economically viable, but they might become economically viable if you will couple them. So here we see that the electricity costs are being reduced, but you see even a more dramatic effect on the manufacturing expenses if you look at, for instance, in paired electrolysis, you increase the production capacity of electrochemical cells and the appendages. So then you think of rectifiers, pumps, and so on. So you can really reduce the operational expenses and the capital expenses of electrocatalysis if you compare 2 reactions in a single cell. So can you just couple any oxidation reaction to any reduction reaction? I think there are 2 aspects to look at. And of course, the first one is the economic or the market aspect. So you should think about 2 processes that have comparable market sizes. You can, for instance, also imagine coupling an oxidation reaction with the production of hydrogen. And electrocatalytic production of hydrogen is believed to become very big. Even so big that there is not a single oxidation reaction that will match the scale. So therefore, it's good to differentiate the anodic reactions and develop multiple anodic reactions that can be coupled with, for instance, hydrogen production. I also believe that it can be very helpful if there's synergy between the anodic and the cathodic products. So if you look at this first image, you create 2 different products at both electrodes. This can be viable, but you have to, of course, also imagine that if you address different markets with these different products, you have to increase your business development efforts. You require a different infrastructure. I think it can be very good if there's synergy between these 2 reactions. So, for instance, here you have convergent paired electrolysis where the products at the anode and the cathode combine to a single product. Or you can think of transforming the same substrate to different products or different substrates to the same product. So these are some economic aspects, but I will talk more about the technical aspects. So a few technical aspects is, for instance, that crossover of compounds can occur through the membrane. So imagine if you are making a product at the anode, some of this anode might transport through the membrane, and this can be difficult for downstream processing, or you might reduce the product that you just oxidized at the anode. So this is something to take into account. Of course, pressure and temperature should be compatible, but now I will talk about the pH compatibility. Just as a start, very basic, if you transport electrons from one electrode to the other electrode, you also need to transport ions. And this this goes through a membrane quite often. So you can transport anions to the anode and cations to the cathode. And in the very simple case of water oxidation and hydrogen evolution, here you consume protons, so you make hydroxides. You can transport hydroxides, or you can transport protons that you produce at the anode. And which type of transport is often dependent on the type of membrane that you use. You can have cation exchange and anion exchange membranes. So this is in the case where you can have proton transport. But then looking at synthetic oxidation reactions, and I've been looking into this for a few years during my work at Avantium, and I actually found that synthetic oxidation reactions are more abundant in alkaline electrolytes. So I don't really see anywhere where I don't really know why this is. I can speculate, I can give some reasons. For instance, that non-noble metals are not stable in acidic oxidative conditions. So for instance, metals as nickel or iron, but also carbon, it will oxidize if you use them as an anode in acidic environment. Also, oxidation reactions are thermodynamically easier in base, and anionic species are easier oxidized. So if you have highly alkaline conditions, you can deprotonate something, make an anionic species, and that can be easier oxidized. So here you have an example. Often when you look at bio-based compounds, they contain an alcohol, and you might want to oxidize this to the carboxylic acid. In alkaline environments, this is quite easily done with nickel-based anodes, but I see very few examples where this is done in acidic medium. So what is the impact on the process then? Here at the anode, you see the reaction that I showed before. So you oxidize an alcohol to make a carboxylate, and with that, you produce protons. But as I said before, the pH for this reaction is high. So in the bulk of the solution, you have this reaction occurring where the protons that you generate at the anode react with the KOH to produce water and to liberate potassium. And it's not a proton that will transport through the membrane, because the proton concentration at pH 13 by definition is very low, but it's going to be potassium that's being transported. At the cathode, protons are being consumed and you produce hydroxides. In the bulk, this potassium that's transported from the anode will combine with the hydroxide and form KOH. So this has the following effect. At the anode, you will decrease the pH, and at the cathode, you will increase the pH. Here you are producing protons and replacing potassium. Here you are consuming protons and you're replacing the protons with potassium. So this requires input of acid and base for pH correction, and this is very costly in an industrial process. Another option is to use bipolar membranes, and these are designed so that you can have ion transport and it doesn't require correction of the pH. However, these bipolar membranes, they are developed for lower current densities. So they are developed for current densities between 40 and 80 milliamps per square centimeter, and often they increase the cell potential. So we're also looking into if bipolar membranes are feasible at current densities higher than 200 milliamps per square centimeter. But it could be that this is the weakest link in the electrochemical cell. So at PERFORM, we are looking at oxidation reactions to be performed in acids, because these are easier to pair with reductive processes. For that, we have developed these lead dioxide-based anodes, And this is special material because this is very stable in acidic electrolyte, even under oxidative conditions. It has a very good conductivity and it has a high overpotential for water oxidation. So you should imagine that if you want to oxidize an organic substrate, this is often in competition with the oxidation of water. On lead, the oxidation of water is not favored, so you can have higher selectivity for the oxidation of your organic substrates. And this is also what we see when we test it with furfural oxidation. So please note the conditions under which we do this. It's 0.5 molar sulfuric acid, so it's very acidic. And we work at 100 milliamps per square centimeter. And because we work in acidic medium, we can use cation exchange membranes, which are well developed and can go up to very high current densities, way higher than this 100 milliamp per square centimeters. Then what we see, actually we see two products being formed. This compound here, which is called hydroxyfuranone, and we form maleic acid. If you add up the Faraday yields of these compounds, we are close to a quantitative Faraday yield, so close to 100% Faraday yield, which I think is very impressive result. Of course, I mentioned before that the target molecule is this maleic acid, and we also make this intermediate, which is the 2 electrons less oxidized version of maleic acid. So what can we do with this? One possibility is to oxidize this with oxygen to get to maleic acid. So if we add another unit operation, we might be able to go to quantitative yields of maleic acid from furfural. But as the project continued, we also looked more into this compound, and we actually saw that this is a very interesting organic compound. You have an aldehyde type functionality here, you have a double bond here, and this alcohol. So it has many functional groups with which you can do organic transformations. However, there were very few examples in literature of this, so the market for this compound is small, but it may in turn become a valuable compound. And this is also supported by a recent publication in Science Advances, where this compound is condensed with alcohols, and here they make polymers and coatings from this. So I think this is a nice example that we target maleic acid. We found something else, and the other finding may be very interesting as well. So the outlook in PERFORM, Roman already showed some of this. Now we are working on 10 square centimeters. And the results that I just showed were all done in batch. So to upscale this, we want to go to 1,000 square centimeters and eventually go to a stacked cell where we go to 1 square meter of electrode size. Steps that we have to take, of course, are translating a batch process into a continuous process, increase the product concentration to make it feasible for downstream processing, but also study the stability of lead. We had lectures before in this meeting already where we saw that lead can leach into solution, but I feel that we made quite a stable anode, but this needs to be confirmed still. So to conclude this presentation, I think there are a few take-home messages, and one is that paired oxidation and reduction reactions can make both reactions more feasible. So again, an oxidation reaction by itself and a reduction reaction by itself might not be feasible. If you combine them in paired electrolysis, you might have an economically feasible process. Synthetic electro-oxidation reactions in acid are scarce, but easier to pair to a variety of cathodic processes. So I can also imagine that the reaction that we show here can be very well coupled to the production of hydrogen or the reduction of CO2 at the cathode. But as I also said before, the market size of maleic acid, that might be substantial, but the market size for hydroxyfuranone is still quite small. So we should study these lead-based anodes and see if there are other reactions that we can do with them, because I think they have very interesting properties as anodes for paired electrolysis. So to conclude, I show a picture of the PERFORM consortium. I think it's a very nice group of people and institutes that is very versatile, and it's a pleasure working with this consortium. I hope to meet everyone in face to face again soon. So this is the end of my presentation. I thank you all for your attention, and I thank the organizers for the invitation to present the work. Thank you very much.
Very much, Bart. And I agree, that is a very attractive looking group of people from the consortium, everyone with a wonderful smile. So thank you for sharing that with us. Now we've come to the end of our session 1, our second segment, which means that we now have time for our questions. So I will now pull out the questions I've been given and begin asking, and let's see. Remember, if you have any more questions or throughout, if you'd like to ask, remember what the procedure is. Make sure your screen is not full screen, then you'll see the option for info where you'll find the program. You also have a chat where you can give anyone, you can give us all, everyone that's watching can see a link or anything else that you might want to post there, a comment, a suggestion. And finally, there's the Q&A. That's where you need to write in your Q&A, as you've been doing, but we want to see everyone participating. So please write in the Q&A questions and we'll get them to answer, either directly on the screen or indirectly. They will answer later via email or chat. Okay, so moving on. My first question is for Bernd. Okay, it says, regarding integration into the intermittent renewable energy system, how are you handling these?
Currently, the problem basically is that if you have intermittent power, you can lose the power relatively quickly if the sun stops shining or wind stops blowing. So we currently implement a battery pack in between the system to facilitate a controlled ramp down of the process to transfer it into a safe operation. And then we just leave it there. And when power is restored, then we just ramp it up again. So it's surprisingly easy with the current process. And we tested it frequently when we run the commissioning of the plant. So it's much easier than anticipated.
Answer, Bernd. Now a question for Roman. Roman, how generally applicable will the PERFORM Power platform be for other electrochemical conversions or reactions?
I'm hearing echo. In this project, actually, the focus is to develop a flexible platform. That's the whole focus of the project. So looking at the reactor, we are developing a flexible reactor where you can change properties of the reactor, such as you can change distance between electrodes, but also you can change the type of the electrodes you would like to test. So we have flexible electrochemical reactor system, but at the same time, from the downstream processing view, in this project, we looked in a generally applicable DSP technologies such as crystallization, extraction, distillation, electrodialysis, for instance. So I think these technologies will be quite applicable for other electrochemical transformations. One thing which is important to mention, so far we focus on aqueous electrochemical reactions. I think this platform will be a bit more challenging for non-aqueous electrochemical systems.
Okay, fine. Thank you for that answer, Roman. Our next question for Bart. You spoke about a bipolar membrane. Can you explain how such a membrane works?
Now, a bipolar membrane that has two layers. It has an anion exchange layer and a cation exchange layer. And the anion exchange layer is facing the anode. And at the interface of these two layers, there is water. And the water fills the positive potential of the anode and the negative potential at the cathode. And because of these potentials, the water can be deprotonated. And that way the hydroxide anion can go to the anode and the proton can go to the cathode. So this is a way to make anions still go to a very alkaline medium. But you have to pay an energy penalty to deprotonate the water, to pull the water apart.
Okay.
But this is a very good method to run a process with the pH conditions that I told, without having to correct for the pH.
Fine. Thank you very much, Bart. That's a great answer. Now, the next question for Bernd. Bernd, given the high water content in the system, how do you minimize separation costs during scale-up?
I believe that is one of the key challenges you have in most of the biorefinery processes we are looking into. Getting rid of water and getting rid is carefully chosen. It's one of the hardest problems. The workhorse in industry is distillation, and in our systems it will not work because you will use a tremendous amount of energy. So we have been looking into membrane processes to basically just concentrate up the mixtures. But what we see now is currently there are few to no membranes available which are applicable in the conditions we are working in, because we have quite a lot of, in our case, quite a lot of sodium ions there, which gives a high osmotic pressure. So we need to find a more elegant way to do that. So currently we're working with removing some of the sodium by precipitating it as sodium carbonate or sodium bicarbonate, and then use membranes, quite simple desalination membranes, to remove some of the water of it, and then we get a more compact downstream system. It's not a very elegant way, but it's a workable way.
Okay.
And I believe, Roman, you have more or less the same challenge.
If you'd like to add.
Exactly. I mentioned in my presentation, so it's quite important. We are also looking in the membrane processes to pre-concentrate our products before the actual purification or separation of the products.
Thank you both. And Bernd, I'm fixated on the photograph the image you have behind you. Obviously, it's a fixed image on your Zoom, but is that an image that you see regularly? Is that somewhere on your way to work or from where you work, or where is that picture taken?
It's basically a composed picture. It's part, the mountains in the back, it's called Lyngalpen. It's in the far north of Norway, where you basically have snow from the mountaintops to the sea. And then the other pictures, they kind of symbolize what Sinta was working in, from marine environment, aquaculture, shipping, oil platforms, wind power, bridges, community, architecture. So yeah.
Okay, so it's a corporate from the company. It's kind of a corporate image prepared there. Wonderful. Well, it looks great. It looks like an interesting place to be, as long as you have a very heavy coat. Well, maybe not today, but
it depends on. It's not that bad. So we don't have any ice bears roaming in the streets, at least not where we live. And yeah, but it's a nice country to live in.
Okay, wonderful. Thank you, Bert. Now let's move on to the next question. This one would be again for Roman. What is the biggest challenge in the project?
I think in this project and also in many other electrochemical transformations, in my view, is the durability of the system is one of the crucial challenges to overcome. You need to make sure that electrode materials are stable and selective over a long time of operation. And if you don't have that, you cannot scale up the project. So I think it's one of the biggest challenges. And another challenge is actually we are building a flexible electrochemical platform and building a TRL6 flexible production skid. It's a quite challenging task, as chemical engineers who like fixed conditions and not that much of flexibility, I would say. So that's another challenge.
Okay, well, thank you very much for that answer. And the final question before we move on to the next session, session 2, is for Bart. Bart, are there industrial processes in which paired electrolysis is done?
So there are some processes in which organic electrosynthesis is done in paired conditions, but very small scale. But I like to think about the chlor-alkali industry, which is a huge industry, of course. And there you also make chlorine at the anode, so useful product. And at the cathode, at the same time, you make caustic soda and you make hydrogen as well. So actually, this is a very large process that generates 3 useful products from a very simple feedstock. So I like to see this process as being a paired electrolysis as well.
Okay, thank you. Well, all I have left to do now is to thank the 3 of you for your presentations. Thank you, Bernd, Roman, and Bart, for your excellent presentations. And we now will move on to our last segment, session number 2, which is entitled New Challenges. Okay, our first presenter for this will be David Cantillo. He will be giving the presentation Greening API Manufacturing with Electro-Organic Synthesis. He is assistant professor at the University of Graz and the area leader at the Research Center Pharmaceutical Engineering. Very briefly, electro-organic synthesis has been shown as a promising strategy for the development of greener methods for the synthesis of APIs, as the use of large amounts of oxidizing or reducing agents can be avoided. In this presentation, we will see selected examples from this group. So, David, the floor is yours.
Thank you very much, Eddie, for the great introduction. Before starting, I would also like to thank the organizers for the invitation to present into this event and for the opportunity to share some of our research in electro-organic synthesis. From the previous talks today, I think it's very clear that electrochemistry is becoming increasingly important in the chemical industry. But indeed, this is something also that is happening perhaps more slowly in the pharmaceutical industry. In the pharmaceutical industry, electro-organic synthesis is seen mainly as an enabling technology. In some cases, you can do reactions that are difficult to do otherwise, apart, of course, from the sustainability viewpoint. Perhaps you have seen in the past some of the press coverage on this. There are many advantages for using electroorganic synthesis over conventional chemistry. They have been already explained in previous presentations, so I will not go into detail. To us, there are mainly two aspects. Electroorganic synthesis can be sustainable and cost efficient. This comes from the fact that we are exchanging stoichiometric amounts of reagents by electricity, which also, of course, affects the price. And I say it can be sustainable because electroorganic synthesis is not always the most sustainable way to make a product. For example, if you need large amounts of supporting electrolytes or you need expensive electrode materials, in some cases it's not really advantageous. And on the other hand, it can also be enabling. This is because you can essentially at very mild conditions produce high energy intermediates such as radicals, carbocation, or carbanions, and also you can be very selective in some cases. Another very important advantage of using electrochemistry is that it's a technology that is relatively easy to scale up. Of course, for this, you need to use flow cells. The use of flow cells has also been covered in previous presentations, so I will directly, since the basics of electrochemistry have already been covered, I will directly present some examples from our working group, and they are listed here. So I will start with a decarboxylated acetoxylation of amino acids. I will also show you how we have synthesized electrochemically C19 androgens. And at the end, I will show our results on electrochemical end-dimethylation of morphine and alkaloids. This is the first example, is on decarboxylative acetoxylation of amino acids. The presence of acetyl groups or the introduction of acetyl groups is very important in API synthesis. Indeed, there are over 70 approved drugs that have this moiety. Of course, this often is introduced by simply acetylating an alcohol. In some cases, like in the case of the amino acids, as we will see later, the presence of the introduction of the acetyl group is usually done to provide a good leaving group. So later on, in a second step with a nucleophile, you can get to this type of structure here. Of course, in this case, when you want to do this with amino acids, it is best to start from the corresponding amino acid and directly do the electrolysis. There are several methods for doing this type of transformation using traditional reagents. In all cases, we have oxidizing agent, typically as an acetate salt. And indeed, the classical commonly used method in the past in industry was to use excess amount of lead acetate to do this type of decarboxylated acetoxylation. As you can imagine, this produces a large amount of lead-containing waste, which nowadays is not really acceptable anymore, at least in Europe. So what we wanted to do here was to provide an electrochemical method in which we would do this decarboxylation and attach the acetoxy group. Decarboxylative functionalization of compounds is known. If you follow a radical mechanism, this is called the Kolbe reaction. And if what you do is to attach a nucleophile, it's called the Hoffer-Most reaction. The Hoffer-Most reaction is typically done with alcohols, so you could form the corresponding ether instead of the acetoxy compound. And we wanted to see if we can also use electrochemistry for doing this reaction. And indeed, it worked very well. So this reaction was developed in collaboration with one of our industrial partners. And here you can see already the optimal conditions for the reaction. So we used graphite and stainless steel as inexpensive electrode materials. And we did this in acetic acid as the solvent with a small excess of sodium acetate as a base and also as a nucleophile. So essentially you have your nucleophile as a solvent here. This, of course, make the reaction very selective. So we could do this chemistry for several amino acids with, in many cases, quantitative yields. And most importantly, what we wanted to achieve is some APA intermediates. And here are some examples that we developed. For example, for making tetramethene, you can do this intermediate electrochemically. Also for phenolphthalein, which is anti-epileptic, or for this dopamine antagonist. So as I said, we got very good to excellent yield in most cases. And as you see, we only needed sodium acetate in acetic acid and electricity to do this reaction, which otherwise needs large amounts of metal containing compounds. Also, as you see here, we could do benzylic acetoxylation using exactly the same conditions, and this could be also interesting for the synthesis of, for example, alcohols from the corresponding aryl acetic acids. After developing the chemistry, we transferred the conditions to continuous flow. In this case, we wanted to achieve a scalable process, and we could do that indeed in a single pass. So using a usual parallel plate reactor, the chemistry could be done in a single pass with actually a very good isolated yield of 94%. And the conditions were more or less the same. The main difference is that we switched graphite to impervious graphite, which is a resin fill type of graphite. And we did this mainly to avoid reaction mixture going through the pores of the graphite, which typically makes the residence time distribution a bit broader. So with impervious graphite, we usually get better results. Another advantage of working in a single pass is that the residence time inside of the reactor is typically quite low. In our case, was around 1 minute. And then, since the residence time is so low, you can easily build these optimization graphics in which we can optimize the flow rate, charge in Faraday per mole that we apply. This is done by changing the current. And you can get your optimal conditions very easily in essentially 1 or 2 hours of lab work. This is how the reactor looks like. It's quite compact because we did this in a small scale. So some important data is that we could increase the yield from 90 to 94%. We also did this in recirculation mode, and the yield increased further to 98. And the space-time yield of the process was 100 times higher in the flow cell. We could, of course, do this in a gram scale. And this is also very important for a scale-up. This reactor could be running for 12 hours without any interruptions, and conversion was completely stable. This is something that we are doing quite often now. When we develop a process, we like to calculate the green chemistry metrics in order to see whether the process is really advantageous. In this case, I think it's quite obvious that doing this electrochemically is highly advantageous compared to using lead acetate. You only have to see that, for example, for making 1 kilo of this product, you would need 3.2 kilograms of lead acetate. Of course, this will generate large amounts of wastes. So what we did is to compare the green chemistry metrics, both qualitative and quantitative, and in essentially all cases, the electrochemical method was a great advantage in this case. The only issue that we saw was that the acetic acid that we are using as solvent is slightly corrosive. Apart from the sustainability, of course, we analyzed the costs, and you have here the numbers. If you compare the price of the electricity that we need and sodium acetate per kilogram of product, the price would be two orders of magnitude lower than the other process, which uses lead acetate and copper acetate as a catalyst. The next example that I want to share with you is about the synthesis of C19 androgen steroids. C19 goes for the number of carbons of these steroids, which are actually very important APIs. There are over 40 marketed androgen steroids of this type. Probably the most popular ones are testosterone or 11-oxo that I think you can buy quite easily. It's you don't need a recipe to buy this. It's some kind of supplement. So to prepare this type of compounds, I think nowadays the preferred industrial route is the microbial degradation of phytoesterols. This starts from natural products and gives you the 17 ketoesteroids. Unfortunately, the disadvantage of this is that the yields are quite low and the process is quite slow due to the low solubility of the starting materials in water, because this needs to be done in water. In the past, there was a route which I believe is not often carried out anymore in industry, and it starts from the corresponding corticosteroid. And what we do here is to cleave the side chain of the corticosteroids to get to the 17 keto compound. And then you need to further processes to your final API. The disadvantage here, apart from you need quite harsh reagents and conditions, of course, you need to quench the whole reaction mixture to get rid of the reagents and make a workup before you can continue with your synthesis, which of course make the process very, very unsustainable. So what we thought here is that if you can do this with such strong oxidizing agents, probably since the skeleton of the steroids is relatively stable, you could do this by direct anodic oxidation. So this is what we did. And again, as you see here, the optimal conditions, it worked very well. So again, only using simple and inexpensive graphite and stainless steel as electrodes, we could achieve this transformation actually in quantitative yields for most of the typical corticosteroids. Also, this was very interesting. We could do the same without the hydroxy group in the side chain. This is something which makes also an advantage of this process with respect to the traditional reagents, which often need the presence of a hydroxy group here. And then finally, we also for this chemistry did a gram scale demonstration. In this case, we didn't do it in flow. We did it just in a larger batch cell, just taking care that the electrode surface to reaction volume is more or less the same as in batch. For this chemistry, apart from the sustainability aspects, very important thing is that it's reagent free. So as I mentioned before, in the traditional reagents, you need to quench them and you need to do a workup before you can continue with your synthesis. Since here we didn't have any reagent, we only have a supporting electrolyte, which is anyway chemically inert. We could do multi-step synthesis of steroids directly in one pot. So what we did is to electrolyze our corticosteroid and directly add more reagents into the cell after the electrolysis was finished. So in this way, we could achieve, for example, a ketone reduction in quite a good yield. Or we did even a multi-step electrochemical sequence. So we cleaved our side chain here. And then what we did is to add tempo after the first step was finished, and without stopping the electrolysis and keeping constant, or no, even increasing a bit the current, we added the tempo, and then we could subsequently oxidize this alcohol to the corresponding carbonyl group, also with a very good yield. And finally, for this example, there was something that other speakers have mentioned before. Typically, you produce hydrogen as a byproduct when you are doing anodic oxidation. This is due to the reduction of protons that you are doing simultaneously. We also were interested in the synthesis of these saturated steroids. And we thought that since this is known to work under hydrogen atmosphere with a palladium catalyst, we thought, what if we directly add palladium and charcoal to our electrolysis cell? So then the hydrogen that is being produced at the cathode can be utilized for this. So this is what we did. We did the reaction under more or less the same conditions. We added a bit of 10% palladium and charcoal, and then we capped carefully the vial so that the hydrogen cannot escape with paraffin. And indeed, we could get the two reactions happening at the same time with almost quantitative yield. The next example that I want to show you from our group is about the removal of the N-methyl group from morphine and alkaloids. This is a reaction that it looks quite simple, but it's not difficult, it's not easy to make, sorry. And actually it's the key step in the synthesis of several opioid drugs like naloxone or naltrexone. As you see here, these are the classical methods. In all cases, you have quite nasty reagents, toxic, like cyanogen bromide, oxidation agents, or chloroformates. I believe nowadays the standard procedure uses chloroformates to do this. And as you see, in all cases, what these reagents are doing is to retrieve the electron density of the nitrogen, so similar to an oxidation. And then this is always followed by hydrolysis. So we thought this actually is known to be possible to do electrochemically. This is the so-called zone oxidation. So our idea was to directly, anodically oxidize the M-methyl group to the corresponding immediate cation. And since we have in the position 14 of the opioid hydroxy group, we thought this will cyclize to this type of oxazolidine. And we knew already that this type of oxazolidine, just by an acidic workup, will give you the corresponding NOR compound, which was our target. In this case, I am showing a bit of the reaction discovery and optimization that we usually do for such, when we start to do such investigation. So we started with cyclic voltammetry of the starting material, which is oxycodone. The reason for this was to find out, because we have two functional groups which can be oxidized. We have the M-methyl group, and also we have the aromatic compound, which is actually activated by the methoxy. You have seen from the presentation of Professor Waldvogel that this type of moiety tends to dimerize. So indeed, what we see in the cyclic voltammogram is that first is oxidized the M-methyl group, and shortly after the aromatic group. And when this would happen, we start to get dimers. So then what we did is to optimize the reaction conditions. In all cases, we screened several electrode materials, supporting electrolytes, and solvents. And in the end, what we found out is that using acetonitrile, methanol, and the usual ethyl ammonium tetrafluoride salt as a supporting electrolyte, we could get the corresponding oxazolidine, which can be later on hydrolyzed in quite good conversion and selectivity. So as you see here, selectivities were always up to 94, 95, 96%, and the remaining 5% is formation of a dimer in the aromatic group, which is something that, of course, we wanted to avoid. So these are, again, the optimal conditions using, as I mentioned, as usual, graphite and stainless steel as electrode materials, and a bit of excess of charge. So the current efficiency was also quite high for this compound. We did this initially with ICA Electrosyn reactor, and as in the previous project, we then transferred this into a flow cell just to make sure that we can later on scale this up. And yeah, we use the same flow cell that you have seen before. If you are interested, we have published the design of the flow cell quite recently, with a lot of supporting information, so you can build this cell on your own. So again, if we compare the two processes, the standard process which uses ethyl chloroformate with the electrochemical reaction, is actually quite striking how this electrochemical process is really an advantage. You need 6 equivalents of toxic and corrosive reagent in the traditional route, and you are producing 15 kilograms of chemical waste without taking into account the solvents per kilogram of product. And also you need 50 liters of water for neutralization and quench of the reagents. In the electrochemical reaction, you only need 144 grams of supporting electrolyte, which in principle is potentially reusable per kilogram of product. And the electricity needed, which is per kilogram 0.6 kilowatt hour, is at least 2 orders of magnitude cheaper. So we are actually looking into commercializing this process, and once we wanted to look into that, actually we thought that this should be even further improved. So there were several things that we were not completely happy about. One is the presence of the supporting electrolyte, 0.1 molar. So I believe this would be actually a cost driver for such process unless the supporting electrolyte can be recycled. And the other point was acetonitrile. So we would have preferred to use a non-toxic solvent. So we were looking into different reaction systems, and here are our improved process that we have now. If you remember the cyclic voltammogram of the starting material, I mentioned that after the oxidation of the N-methyl group, you have the aromatic compound, which can be also oxidized, forming dimers. Formation of dimers was one of the things that we wanted to avoid. So the trick here was to add an additive, which was potassium acetate as a supporting electrolyte instead of the ammonium salt. I'm sure you have heard in the past that when you want such a process to be selective, you need to work under constant potential conditions using a reference electrode and choosing the potential of the group that you want to oxidize. This is a problem for scale-up. So scale-up is typically done for constant current processes. And this is a trick that we have made to add the acetate as a supporting electrolyte. Once the N-methyl group is consumed, before the aromatic ring would be oxidized, we have this supporting electrolyte, which actually is being oxidized as in a potential that is before the aromatic ring. So essentially, we avoid completely doing this trick, the formation of the dimer. So when we would have full conversion, we start to oxidize potassium acetate, which I think release ethane, CO2 as byproduct. So by doing this, we could essentially get quantitative yield for the oxazolating intermediate, which will also give more or less quantitative yield for the product. We were able to increase also the reaction concentration from 0.05 molar, which is very diluted, to 0.2 molar in ethanol. Again, we change an expensive supporting electrolyte by potassium acetate, and we increase the yield by eliminating the formation of byproducts. These are some additional chemistries that we have studied in the past 2 or 3 years in our group. So in case you are interested, I leave you here the references. So we have been working a lot with 3-fluoromethylations, also alcohol oxidations, and these are examples actually that we have already seen. And we have also done some methoxylation. So to finish, I would like to thank the whole group at the University of Graz and the RCPE. Of course, especially the guys who have done all this work, Gabriel, Wolfgang, Manuel, and Florian, our funding agencies and our industrial partners that are funding this work. Thank you for your attention.
And thank you, David, for your presentation. That was the first of our last session, and we have coming up now the second presentation, which will be a bit different, only for the reason that we have 2 presenters for the next presentation. So the title of the presentation is Bio-based Feedstocks to Chemical Building Blocks, Design and Technical Feasibility. Our 2 presenters are Mr. Joost Helsen, Project Manager at Vito, and Mr. Gabriel Centi, Professor at University of Messina. Now, this presentation takes a look at the process of glucose electrooxidation to glucaric acid, as well as its industrial relevance and the general aspects concerning the catalysts and mechanism. So we're going to begin with Gabriel. Gabriel Centi will start the presentation, and approximately halfway through, he will hand it over to Joost Helsen. So if you're ready, Gabriel, you can take the floor.
The presentation before on performance is one part of the overall process to go from glucose to adipic acid, which is, let me say, is a very important on million scale process realized and of course very optimized up to now, but which can be made in a different way, starting from glucose rather
excuse
than
me,
from
I'm sorry.
fossil fuels,
Gabriel,
and also these processes
Gabriel,
and a number of. Yes?
Gabriel, I'm sorry to interrupt you. I just wanted you to know that they didn't see the very start, the first few sentences, so maybe you would like to go back and start from the beginning. I apologize, but you began a little bit too soon. Okay,
but
thank
this
you.
is fine, because this I was starting from very brief to introduce the topics. Now you heard me? Yes? It's fine?
Yes, fine, yes.
Yes, okay, perfect. So I will very briefly introduce the topics of glucose electrooxidation to glucanic acid, which is a part of a new process to go to adipic acid. We have seen before, this is the overall process that is studied inside the PERFORM project, but also is itself an important topic. And I will very briefly introduce what was the starting point for the project and some aspect of also reaction mechanism and first catalyst trainings. And then next slide. Just will go more specific in dealing about some specific aspect about how we realize the electrode, the flow cell, and also up what are the state of upscaling to kilogram scale. Next slide, please. Glucose electrooxidation to glucanic acid, and you see on the top right also the molecules, for who is not a well expert, essentially is the, in some way, opening and oxidation of the basic sugar, which is glucose, is itself is an important product, because there is also a growing market, which is estimated to arrive to something like 1.5 billion in 2027, because it's used in detergents, spreaders, food ingredients. So it's itself a good market. Today is produced by glucose oxidation using nitric acid. And of course, as usual, when you have nitric acid, you have a side product in terms of NOx, you have a side products is a stoichiometric reaction, and so is not a very green process. You can make this also using biocatalytic process. The problem is that up to now, still selectivity are very low, and also rate are slow, and there is a main problem of separation cost. Can be made also catalytic. Essentially, the best catalysts are alloy of platinum and gold. They need to, of course, to operate under high oxygen pressure. Best yield is around 50%. But the main problem which exists is due to the fact that you need to operate under high pressure and higher temperature. You need to have special material for autoclave, because of course this is the acid, and so it's quite aggressive. And finally, electrocatalytic. Electrocatalytic is, again, is an opportunity to decrease capex and opex and impact also for this. Next slide. But especially how we see here, this is part of the PERFORM project, is possible to combine with the hydrodeoxygenation on the other side of the paired reactor, and we have already seen that there is a very clear advantage in pairing the reaction, because of course you reduce the cost, and also you reduce you make two reactions in one single reactor. And of course, in the total, you can go from glucose to adipic acid, which is a very large on million ton scale product, because it's one of the reactants to go to nylon 6,6. So this is a very green process, and we call this green square process, because you use both renewable feed, because you use glucose and also renewable energy to make a very interesting process in which it's possible to have in one single step the process. With respect to another competitive project that was developed by Renovia, which also starts from glucose, there are advantages because, of course, you have an intensification of the process because you realize two steps. In one single steps, you have advantage in terms of energy because you run one single reactor, and also you avoid to feed oxygen from one side and hydrogen from the other side, so you avoid all the impact that you have to produce, for example, hydrogen that is today is produced from fossil fuel. So, and you have several potential advantages which make this also very feasible for small scale production. Next slide. When we start the process, it was very few study on the topics, because let me say that there was several study, but only dedicated to full oxidation of glucose, essentially for glucose direct fuel cell. And this, of course, was essentially noble metal based or some Renithat electrocatalyst or palladium based alkaline. But in this case, of course, the target was to have full oxidation, so to produce carbon dioxide. Next slide. If we looking on the contrary to have a selective oxidation, there was very few data, and essentially only this one that was using a porous manganese titanium electrode. You see that was a kind of tubular reactor in which you was essentially passing through the tubular porous titanium electrode, and on which was deposited the manganese oxide. And the result was something about 35% of yield of gallium glucosic acid. But the problem is that this was working only on very diluted glucose solution. And of course, for this reason, very low productivity and of course, difficulty, because you need to pass through the porous system, and so was not the productivity itself is very low. We have some additional results most recently, but before to introduce these, I like to say that also another old result was on using on tempo-mediated electrooxidation that was giving very good yield, and we will come back on this aspect. More recently, it was very few results essentially dedicated to noble metal catalyst. And also using of nickel hydroxide catalyst that we was also try to develop and to study. In terms of reaction mechanism, you see that glucose is essentially a multi-step oxidation. So in different steps to go to glucaric acid, you have a first step to electron oxidation going to gluconic acid, a second to electron oxidation to glucuronic acid, and finally a further to electron oxidation to glucaric acid. So in total is a 6 electron oxidation. So it is a bit difficult transformation. And of course, there are various byproducts which are possible. Here are listed some of them, but especially the problem is that you have a completely different behavior when you go from very diluted solution to more concentrated solution. And of course, from industrial application point of view, is interesting to go to more concentrated solution, because otherwise the productivity are very low. And in this condition, also, when you go to more concentrated solution, there is, of course, problem of stability of the electrocatalyst, because for two reasons. First is that you have many side reaction which can start between these various compound, and of course, this will also depend on the pH of the solution. For example, you can form some heavier product like humic, like that you can control, going, for example, to very strong basic conditions, but which are not very suited for industrial operation. And also, glucaric acid is the acid and a very good complex agent. So you can imagine that mostly of the catalysts have problem of stability in this condition. Next slide. So it was a very challenging reaction, and as I mentioned, this is a very large scale, and the comparison is on already well optimized catalytic process. So we start with some of the results, taking some of the catalysts that was more or less similar to the one that we have seen before in terms of literature. But you see that most of the results cannot be really reproduced, and also using a variety of different noble metal or non-noble metal, also using either calcite or nickel hydroxide, as mentioned before, that was giving good results. We have not obtained, we was not able to reproduce the result essentially, because this is one typical problem, that when you not go to very diluted condition, but you go to more realistic condition of operation, reproducibility of the literature data was very difficult. So this is the reason why we was moving more to temper reactor that will be presented this part from Justin. Justin, the floor is yours.
Okay, I hope you can all hear and see me. So I will continue with this tempo-mediated oxidation of glucose to glucaric acid. Please interrupt me if something is wrong and either sound or image don't come through. So we did some initial screening tests, as Gabriele showed, with tempo in very small divided cells, which were quite promising actually, as you could see, and we achieved reasonable yields, even quite high, I think, when we had the 80% of tempo. So actually one of the conclusions here was that, yeah, for as far as we could see, at least on this scale of reaction, we observed no poisoning of the electrodes, and we also see that there is quite high stability of the mediator and a very high reactivity. The glucaric acid yield, actually the glucarate yield, since we're working at very high pH, was there to prove it. This is, as you can see, the reaction mechanism of the oxidation of tempo at the electrode, and then the mediated oxidation of the oxidized version of tempo in comparison with, in this case, general primary alcohols, but of course, for glucose, this counts as well. One thing that we considered from the start, and we were a bit reluctant to discover or to engage in this field of mediated oxidation, is that you also have to separate, of course, your mediator from the reaction, or if it's sacrificial, that means, of course, that's an extra cost. And since we were very much focused on having low cost reaction, this was an issue that we wanted to tackle, and I will further explain in the slides later on. So one of the things, I mean, first actually thing that we decided to do to make sure that we didn't lose too much tempo during or after the reaction was to immobilize the tempo. And there is some indication that immobilization of tempo is possible in combination with some substrates. And the route that we decided to follow or to investigate was to see if we could immobilize tempo on a carbon structure. And the carbon structure could then, in our case, be the anode material. So for the amino tempo that we chose in that case, we wanted to have the reaction of the amino group with the carbonyl group on the graphite electrode, and then securing in this amide bond the amino function. So I'm hearing myself now, so I'm not sure if something is wrong. Please interrupt me if I need to retake some part. So the covalent bonding of the amino tempo on the carbonyl groups of the carbon surface could be activated carbon graphite, any kind of carbon. That would be the scheme that we would like to follow. We screened different carbon materials, woven and non-woven materials, with a fairly large surface area. Screened different immobilization times for the reaction of the amino tempo and the substrates, and also different concentrations of the amino tempo. We had one of the, let's say, the most optimistic result that we had was mentioned here below, where these are the conditions. I will maybe not go into detail, but the main important thing was that although we did achieve some yields to gluconic acid, we did not detect any glucaric acid. So basically, only the first step of the oxidation was carried out, and the final oxidation of gluconic acid to glucaric acid was not happening at those immobilized electrodes. So therefore, we chose to really go for the mediated tempo glucose oxidation reaction, and we did this in microflow cells. So this is what basically the first scale up, as you can call it like that, from the small divided cells of around 80 milliliters to microflow cells of around 10 centimeters square of area. I'm still having a lot of echo. I don't know if anyone can solve this. We check the variables in terms of tempo, concentration, temperature, anode material, and electrolytes. To give you an idea, so this is the flow cell that we use. This is kind of the setup, where just catalyte and anolyte are pumped in two separate vessels, and a membrane is put in between. Also, we studied a few membranes to see the behavior, but that was not, let's say, the main decisive parameter. Here you can see the two types of, we investigated many electrodes or carbon materials, but these are the main two types. So we have a non-woven carbon material and a woven carbon material, and on the right a non-woven felt activated carbon. So in terms of glucaric acid yields during these experiments with the different types of electrodes, these are just numbered, and WACF means woven activated carbon fiber, and NWAC means, of course, non-woven activated carbon. There we see for most of the non-woven materials, we see a good to even very good conversion of glucose to glucaric acid. And when we consider the concentration of tempo that we add to the reaction mixture, there is not really a clear relation between the concentration of tempo and the glucaric acid yield, which is maybe a bit counterintuitive, but can also be because of some variability we had we had some problems in reproducing some experiments. So this could be also the case. Anyhow, the glucaric acid yield that we achieved for the non-woven activated carbon fiber felt actually was sufficient to continue and to investigate more the other parameters. The temperature, amongst others, also means a bit like a how to say, counterintuitive that at lower temperature we achieve higher yields, but this is actually also something that we would still like to confirm in larger scale experiments. And there is some indication that this indeed is also the case, is also reported in literature. Concerning the electrolytes, the electrolyte that we initially used was sodium carbonate at a pH of 11.3, but we also thought of downstream processing this molecule, and then an acidification step would be necessary, meaning that we would lose most of the electrolytes in the form of carbon dioxide, and that's of course a bit difficult to it would be, let's say, a bad selling argument for a process which is should be as eco-friendly as possible. So therefore, we switched also to other electrolytes, sodium hydroxides at different pHs. What we tested at this stage, and we see that it's feasible. These are also maybe still need to be confirmed, these tests, but in any case, I think there is a possibility that we can switch to a either sodium hydroxide or even potassium hydroxide electrolyte. Then we had a flow cell experiment during 24 hours where we achieved, let's say, the most optimal conditions, most optimal results. And these were, as mentioned here, so the current density that we achieve is around 15 to 20 milliamps per square centimeter, and a Faraday efficiency towards glucaric acid of nearly 60%. After 24 hours, we also have a yield of 60%. What we see here is that the maximum conversion actually happens during the first hour. So initially, glucose is transformed, converted to gluconic in the first hours, let's say, and then later on it's further converted into glucaric acid. So we have a peak of the reaction rate of glucaric acid at around 2 to 3 hours. This is important, of course, for upscaling in larger reactors, meaning that we have to take into account the residence time, and also the linear flow velocity will be very important. These are the conditions that we used this flow cell experiment. So we have a working electrode with a non-woven counter electrode, and then we start with 50 millimolars of glucose and 100% of tempo. The next step will be the upscaling of this process now to a scale of 1,000 square centimeter, and this is the reactor that you see here on the picture. That probably was also shown before, and that is the single cell that we received from one of the partners of the PERFORM project, and where we will validate the reaction at larger scale. So we will start the first experiments, of course, with 100% glucose, but in the end, it's also the objective to work with feedstocks to work with realistic feedstocks containing also other contaminants that we can then evaluate in the process. So a single cell of 1,000 square centimeters with a non-woven activated carbon that was selected of the previous tests. We will start with 100% of tempo, since we know that for sure will give us the appropriate yield in terms of glucaric acid. And we will control, at least we will try this to change the base that we add to potassium hydroxide, control the pH between 11 and 12. Also, I think in this scale, we will definitely need to redo the temperature study and study also the electrodes degradation. The idea would be that this cell would produce around 20 grams per hour of glucaric acid. Of course, this is still a concentration which will be quite low, and therefore we need this very performant DSP to separate and to purify the glucaric acid. And this will be mentioned on the following slides. So the first step in our DSP that we have envisaged was the electrodialysis. Electrodialysis, I don't know if you are familiar with the process, but it's basically also kind of an electrochemical process. Some call it electroseparation process, where also in flow cells with alternating anion and cation exchange membranes, a certain stream is salts or charged ions are removed from. And the idea here would be that we would remove both gluconic and glucaric acid from our reaction broth, so from the analyte. We tested this already in on the lab, so also in microflow cell setup, meaning this 10 square centimeters, and we achieved the current efficiency of 95% at room temperature. We tested 4 membranes, 4 types of membranes from 3 suppliers, and we see that there is a very good separation actually. So we have a good separation of both gluconic and glucaric acid going to the concentrate side, and the glucose remaining in the diluate side. The maximum achievable concentration that we estimate based on the test so far will be 1 to 1.5 molar. Okay. The next step that we foresee once we have removed these organic acids basically from the analyte is a crystallization step. And therefore, I think it's important that we use indeed potassium hydroxide to achieve the monopotassium glucaric acid from the electrodialysis concentrate. And this could precipitate at around 0.2 or 0.25 molars. If necessary, we can still include a concentrating step, for example, using a nanofiltration or reverse osmosis. But for now, this is not anticipated, since we expect to achieve the combination of the electrolyzer cell and the electrodialysis to achieve sufficient concentrations. So the first step in this crystallization would be the cooling crystallization, where we remove the bulk of the monopotassium glucarate. So this crystallizes and can be removed. And as a second step, this is maybe more innovative solution, would be to add an anti-solvent to this supernatants of the first step, and therefore increasing the yield. And anti-solvent is basically a solvent that is miscible with, in this case, water, but which is a non-solvent for the solute, for the glucaric acid in our case. So the solute precipitates and then can also be separated. We did some experiments with this process, and we used both methanol and isopropanol as a anti-solvent, and we see actually that we have a quite good separation performance, mostly in a pH range between 3 and 4, 3 and 3.7, 3.8 actually. where glucaric acid selectively precipitates. Yields of 80% and a selectivity of 10 is possible. And we can also have an intermediate solid separation and then the subsequent methanol wash, where we actually don't lose a lot of glucaric acid or monopotassium glucarate, but we still can increase the purity. Yeah? So the selectivity increases even further with a washing step. This is then my second to last slide, and this summarizes more or less the elements that I talked about. So this would be our scheme, the SP scheme, and also the reactor is included here for the production of glucaric acid on a larger scale. So we have the electrolytic reactor here. The electrodialysis will be coupled to the electrolyzer and will separate the gluconic and glucaric acid from the anolyte. This will go to a cooling crystallizer where the solid monopotassium glucarate is separated. The liquid from the cooling crystallizer can then be further or the glucaric acid in this liquid can be further harvested by adding the antisolvent, the methanol, which of course then needs to be distilled afterwards. So that's a bit of a, let's say, more complicated step. But still, all in all, I think this could be an elegant downstream processing for the glucaric acid. Okay, to summarize, so the tempo-mediated oxidation of glucose seems quite possible and even at a reasonable performance, although it was not so straightforward. We achieve a yield of around 60% and also 60% efficiency, the Faradaic efficiency, that is. Next step will be the upscaling of the single cell of 10 square centimeters to a single cell of 1,000 square centimeter, and finally to 1 square meter. This is all within the project, and hopefully within 1 year from now, we will be able to produce around 200 grams per hour of pure potassium monoglucarate. We also see that electrodialysis performs a very powerful separation for the glucose, also for the potassium hydroxide, and then the organic acids on the other side. And we have a two-step crystallization as a quite robust separation, where we can still fine-tune the purification by adding antisolvent in different washing steps. This is the end of my talk. I'd like to thank you for your attention.
And thank you very much, Joost, and also thanks to Gabriel for this very interesting presentation that you both gave us, so we appreciate it. Now we move on to the last of our presentations in this session 2, our third segment of the day, and also our last presentation of the day. So we would like to now give the floor to our next speaker. The title of his presentation is Tempo-Mediated Electrochemical Oxidation of 5-HMF for the Sustainable Production of Furandi Carboxylic Acid from Biomass. Now, in this talk, we will hear about the value chain from biomass to bio-based plastics via an electrochemical oxidation route of the intermediate 5-HMF and see a technical and economical comparison with alternative routes. So, our presenter is Mr. Steven Kraveliski. He is head of R&D at EVA Biochem. So, if you're ready, you will have the floor in just a few moments, Mr. Stefan Kraveliski.
So, thank you. Thank you for the introduction. Can you hear me?
Yes.
Good. So, I would like to talk about some things, tempo-mediated electrochemical oxidations for FDCA from biomass. And my agenda would be, I would like to introduce some expertise of AVA Biochem and the mission of AVA Biochem. Our approach to our goal and approach to bio-based plastics, our electrochemical way to FDCA, and some conclusions. So AVA Biochem is especially focused on the conversion of biomass to 5-HMF, 5-hydroxymethylfurfural, which is a platform chemical, a well-known platform chemical. And I will show you in a few slides later how we do this, but only to show you the pathway, the value chain from biomass to 5-HMF. And there are a few applications from 5-HMF. One of those is the oxidation to FDCA. FDCA is a monomer of a lot of different possible polymers like PEF, but also it is a replacement, for example, for formaldehyde. And for example, in formaldehyde-free resins, adhesives for the wood industry, and also for some specialty chemicals in health, wellness, agrochemicals, and food additives. I want to focus on our strategic goal, the oxidation to FDCA and as a monomer to PEF. Why PEF? PEF is a well-known superior polymer to PET because it has some superior properties. For example, in regarding to PEF, we have improved barrier properties for oxygen, CO2, or water. This polymer is 100% recyclable. It has some intrinsic properties which allows, for example, hot filling because of the higher glass transition temperature. It has a higher modulus versus PET, and it is definitely 100 bio-based polymer. That's why we focus on PEF. So the pathway to PEF coming from biomass is, you can see here the value chain. Biomass, we will have a sugar extraction coming from very different biomasses, and a fructose production. And that's our entry point here for our biochem. We dehydrate the fructose to HMF and want to oxidize it to FDCA for polymerization reasons to get polymers like PEF. And we are here in the middle of this value chain. So we think the technology we developed here together with TNO and with the University of Wisconsin is a very good technology exactly for our outcome of the dehydration process. I will show you this in a few slides later, because we have a very economic process, which is easy scalable, and which is because it is 100% water-based and environmental friendly. So let me say some words about, before we come to the electrochemistry, what we are doing exactly at our biochem. What is our core? So we take fructose, and we have a HT, which means a high thermal process, a hydrothermal process, which dehydrates the carbohydrates to HMF. This is a well-known process. It's not a big thing. It's well known this 100 years. But what we are doing then is the purification of exactly this processed water to a well defined purified HMF product. We have some steps of ultrafiltrations, nanofiltrations, and we have some concentration steps of reverse osmosis and evaporation. And at the end, we come to a product which has about a 25% aqueous solution of HMF. Now we are very, let me say, expertised in these processes, and we plant or designed a plant for a 6,000 tons per year capacity, with the numbers you see here, with the capex and COGS and surface area, to seed the market with HMF with a very clear defined quality and for downstream processes. For the next, we tried to compare all the oxidation methods of HMF to FDCA, which is the monomer for the PEF production. And as you can see here, we did a lot of trials. For example, chemical oxidations with heterogeneous catalysis in our own labs and with partners, or in enzymatic oxidations, or in bioconversions in different projects, and also in electrolytic oxidations. And what we found out is that all the processes we compared, we really can say that the electrolytic oxidation process, what we call the MED-LOX process, is the very best in all these figures, the very best process which we can say. I can show you why. A few words about the electrochemical process itself. So as we had in the former presentation, the tempo-mediated reactions is very well known, and we have a HMF to FDCA reaction mechanism, which we together had a search with the University of Wisconsin, and we found out that we have a very good conversion from HMF over the route of DFF to FFCA to FDCA. This is now a very well-known mechanism. What we can see here is there are two different routes, HMFCA or DFF, the route with the tempo-mediated electro-oxidation goes predominantly through the DFF path. We found FFCA as an intermediate, and this is one of the difficult intermediates for the PEF production because it is a chain stopper. So this is only as a reminder for all electrochemists which are here. The tempo-mediated oxidation mechanisms, I think, is very clear. We use a carbon felt anode. We have a PEEK anion exchange membrane and a nickel cathode. And you can see in these diagrams the principle of the reaction. We found out that we achieved here a real, nearly quantitative FTCA yield in a very short time. As you can see, in about 50 minutes, we have close to this 97 to 98% FTCA yield. And this mediated oxidation leads to a kinetics which is really outstanding. Why do we say this is at the moment of the best-in-class process? Because we have a reaction selectivity of more than 90%. We don't have the production of HMF oligomers. In other reactions like chemical catalyzed reactions, we have this oligomers because of this mediator tempo, which is also acting as a polymerization inhibitor. We don't have any interference of impurities in HMF feed with our feed, which comes from our plant. We have an overall electrolysis of more than 97% in the continuous operation. We have a very high raw FTCR purity, which is more than 99% in lab scale. No HMF, which is facilitating the downstream purification process, with a net current efficiency of 97% and a current density of more than 100 milliampere per square centimeter. We have very inexpensive electrodes, which is the carbon felt anode and the nickel cathode. We have in this situation a revenue, if we want to count it from paired production of hydrogen of 42.5 kilo per ton of FTCA. And we have the possibility of a high value reduction reaction at the cathode. The potential revenue from co-products, which is fulloic acid, which we produce definitely also from the other byproducts of our streams, and in the entire process, from the raw biomass, all the things are all done in aqueous solution. So we are very sure that the lowest overall FTCO costs of all our process, chemical, enzymatically, biochemical, and electrochemical, the lowest overall costs we have in the electrochemical process. We have a patent on this, or we are a licensee on the patent on this. This patent covers all nitrogen radical mediated processes, including all electrolytic and photoelectrolytic processes. And the mediated process has definitely significant cost advantages over the non-mediated. And we have granted a worldwide exclusive scale-up and commercialization rights to AVA Biochem. What is our ongoing development project? So in a first phase, we did bench scale continuous process piloting, and we did this together with the University of Wisconsin and TNO. We completed this with a 400 square centimeter electrode, and we calculated the price of FTCA within this scale for 3,000 euro per kJ. Okay, this is a bit too much for FTCA. In a second scale, what we are planning now, we want to reproduce all these results and test batches on existing electrochemical plants and try to isolate and purify this FTCA to a polymer grade with a scale of 3 to 5 tons per year. And we calculate with a FTCA price of 100 euro per kJ, which is at the moment a very good price. If this succeeds, we think, or we are rather sure, that we could meet the market requirements of smaller than 2 euro per kJ in midterm, or smaller than 1.5 euro per kJ in long term, with a scale of 30,000 to 150,000 tons per year. What I show you here, this is our calculation. The blue curve, which you see, is about our rough estimation of the development of the FTCA price. And we try to compare it here with the polymer prices, what makes sense. For example, in the market introduction price, it's probably difficult to have a price of more than 8 euros for new polymers. We think that our calculation leads to, with this technology, this is electrochemical technology of oxidation of HMF, leads to FTCA prices which fits well in this acceptable prices of polymers in the near future or long term. So what I want to say, we think the availability of FTCA will definitely unlock a huge pent-up market for bio-based polymers. And our objective here is to take our output of the HMF production and couple it with the most efficient electrochemical technology to position ourselves to try to be a leading technology provider in this industry. Paralox is not the only possibility for HMF, could be also in other applications. And we think that the electrochemical way is definitely for our purposes and for our output the best way to come to a real to products which are economically and ecologically feasible. Thanks a lot for your attention, and I'm ready for questions.
Well, thank you very much, Stefan, for this, the final presentation of the day. We're running a little bit behind schedule, so we have very little time for questions. So I would ask David, Gabriel, Joost, and Stefan now to be ready. So we're going to ask each one of you just one question so that we can finish close to being on time. The first question is for David. David, you mentioned that the need for supporting electrolytes is detrimental to the sustainability of an electrochemical process. Is it possible to remove it from the reaction?
Yeah, so the role of the supporting electrolyte is mainly to provide conductivity to the reaction mixture, and this is especially important in organic solvents where the dielectric constant is lower than water. There are some things that you can try to do to avoid them. For example, if you have a base or an acid in your reaction, normally this can already act as the supporting electrolyte. In the case of the acetoxylation, for example, we had sodium acetate as base and also a supporting electrolyte. And also, when you run the reactions in continuous flow, the narrower is the gap between the two electrodes, the less amount of supporting electrolyte you need. Because of the low distance, there is less resistance in the cell. And actually, it is possible sometimes to completely remove it when the inter-electrode gap is very small, like in the range of micrometers, then actually removing supporting electrolyte.
Thank you very much. Thank you for that question, David. The next question is for Gabriel. The electrocatalysts presented as analogous to heterogeneous catalysts used for the same reaction. Is it true to assume this parallelism?
Yes, thank you. I think that this was the starting point, and if we look also at several data and literature, this is often assumed. But what we have realized is that this is not true. The catalyst, the electrocatalyst need to work with a different mechanism. And when there is really a parallelism, is because this is not really an electrocatalyst, but is simply an assisted electrocatalytic reaction, which means, for example, there is generation in situ of oxygen or of hydrogen, and then is a catalytic oxidation and a reduction. But if it's true electrocatalytic reaction, the catalyst should be different.
Thank you very much. By the way, I didn't mention your background photograph, but it is quite impressive as well. I hope it's not out of your window, is it?
No, it's the view of Messina.
Very nice. I hope to visit one day. Okay, let's move to the next question for Joost. What would you consider to be the main bottlenecks in upscaling this process as presented?
Well, I would say, again, a lot of feedback. I will try to talk through myself. So for the upscaling, I think the main bottleneck will be the electrolytic reactor. So the DSP elements that I discussed, the electrodialysis, the crystallization, anti-solvent precipitation, they are quite mature technologies and also available at larger scales and also tested. Of course, for these specific conditions, we need to verify, but the electrolytic reactor will be the main bottleneck in scaling up and assuring that we can achieve, let's say, decent current densities, especially, and yields in terms of conversion of glucose to glucaric acid. So yeah, I would say this is our main challenge, I think, for the coming months, to make sure that we can extrapolate extrapolate the results actually of the small scale reactor to a larger scale. Yeah.
Okay, thank you very much, Joost. And Stefan, finally, how do you plan to proceed in this project now?
Well, so we are not the electrochemical specialists, so we need some people who will help us here. There are a few possibilities. So we have some partners which are experienced in electrochemical processes, and there are also some possibilities of EU funded projects. And we are looking at the moment for exactly these partners which can help us either as a professional partner or in EU funded projects.
Okay, well, thank you very much. And that's all the time we have for questions. So what I need to do now is to bring our webinar to a close. And the first thing I would like to do is to thank all of our presenters. Without the speakers, we would not have this source of information for all of our viewers that are, I'm sure, following very carefully everything that is being presented here. So let me just quickly thank everyone, beginning with Angel Zorduña, Siegfried Waldvogel, Carl Friedrich Hoppe, Bernd Wittkens, Roman Latsusbaya, Bart van den Bosch, David Cantillo, Just Helsen, and Gabriel Centi, and Stefan Kraviliski. Thanks to all of you for taking the time to be with us and to share your knowledge, which as we have been able to see is quite significant. And we hope that this will help everyone watching, that will help our society in general to improve the situation that we are currently in. Hopefully all of this will be one more drop in the bucket to improve the ecological and environmental situation of our planet. I would also like to thank Aspire, Liberate and Perform for having organized this webinar. Now remember, the webinar is available, it will be available right away as soon as we finish. It will be posted on the same website that you connected, the same platform that you connected to follow it. So if you want to go back, something that you missed, you want to have a colleague see it, or I don't know if it can be downloaded, but I assume it can. In any case, it will be available there, and I'm sure that Perform, Liberate, Inspire will have it in their social media as well. So, ladies and gentlemen, thank you so much for your attention. We thank you for having joined us. You could have been doing so many other things, from meetings to emails to telephone calls. But you were here with us following these experts that have shared their knowledge with us. So thanks to all of you. And we hope to see you again in the future for another webinar or similar event. Thank you and good afternoon.